At first glance, Io looks like something pulled out of a person's imagination, its surface scorched with molten lakes, towering plumes of sulfur, and volcanoes that never stop erupting. But Io is real. Orbiting just over 400,000 kilometers from Jupiter, Io is constantly pulled and twisted by the planet's immense gravity. The result? A world where the ground is in constant flux, where lava flows reshape the landscape faster than almost anywhere else we know. Io has challenged our understanding of planetary science, helped us measure the speed of light, and raised questions we still can't answer. As we look further into our solar system and beyond, could Io teach us something crucial about where life might, or might not, exist? Let's journey into the heart of a moon that never rests. Galileo's glimpse. Io's place in the moons that changed the cosmos. In January 1610, the skies above Padua, Italy, were clear and quiet. A man named Galileo Galilei stood on a rooftop, hunched over a telescope he had built himself. It wasn't a powerful instrument by today's standards, just a slender tube with glass lenses, but it was enough to open a door no one had looked through before. That winter, with a shaky hand and sharp eyes, Galileo turned his telescope toward the planet Jupiter. What he saw would help change our understanding of the universe forever. At first, he noticed something odd. Tiny pinpricks of light near Jupiter, like stars. But they were in a line, and they stayed close to the planet night after night. At first, he thought they were fixed stars that just happened to lie in the same part of the sky. But then, they started moving. Over several nights of careful observation, Galileo noticed these points of light shifted position. Sometimes one would disappear behind Jupiter, only to reappear on the other side. They didn't stay still like stars were supposed to. Galileo kept watching. He drew their positions night after night in a small notebook, the sketches simple but clear. There was a pattern here. These lights weren't orbiting Earth, they were circling Jupiter. Galileo had discovered something no human had ever seen, moons orbiting another planet. Today we call them the Galilean moons, Io, Europa, Ganymede, and Callisto. At the time, Galileo simply numbered them. Io, the closest to Jupiter, was the first of these wandering lights. It might seem small now, this finding of 4 dots of light through a blurry telescope, but in 1610 it was a revelation. At that time, the dominant idea in Europe came from the ancient Greek philosopher Aristotle, and later the teachings of the Catholic Church. Everything in the heavens moved around the Earth. Earth was the center, the sun, the stars, and all the planets. Everything was thought to revolve around us in perfect circles. Galileo's observation was simple, but undeniable. Here was clear evidence that not everything orbited Earth. Those little dots, moving back and forth around Jupiter, were moons. They didn't care about Earth's place in the cosmos. They followed Jupiter. And if Jupiter could have moons, why not other planets? Why not the Earth itself moving around the sun? These ideas were dangerous in Galileo's time. Saying the Earth wasn't the center of the universe could get you into serious trouble. But Galileo didn't keep silent. He published his findings in a small book titled Sidereus Nuncius, or Starry Messenger, just months after his first observations. In it, he laid out the evidence. He described the moons, their motion, and what it meant for the larger structure of the cosmos. This book caused a stir across Europe. Scientists, philosophers, and church leaders argued over what it meant. Some rejected the findings outright. Others rushed to confirm them, building their own telescopes and pointing them at Jupiter. The moons were there for anyone to see, if they had the tools and the courage. The moons of Jupiter looked like little stars. No detail, no color, no surface, just tiny, shifting specks. Yet those specks carried an enormous weight. They chipped away at 1,000 years of belief in a fixed, Earth-centered universe. They hinted at a wider cosmos, one with other centers, other systems, other possibilities. Centuries later, with spacecraft and high-powered telescopes, we would finally see Io for what it truly is. Not just a moon, but a world of fire and motion, alive with volcanic activity, shaped by powerful forces beyond anything Galileo could have imagined. But on that cold January night in 1610, none of that was known. All he saw was a light moving around a planet. And yet, from that simple sighting came a break in the wall of ancient thinking. From that single observation of Io and its siblings, our view of the universe began to widen. The Earth was just one world among many, and the cosmos suddenly felt much, much larger. Naming controversies, from Medicean star to a volcanic moon. When Galileo first saw the moons of Jupiter, he didn't call them moons. He didn't even call them by their individual names. At the time, they were simply strange points of light near the planet. And when it came time to name them, Galileo didn't choose anything based on mythology or science. He chose politics. In March of 1610, 2 months after his discovery, Galileo published Sidereus Nuncius, and in it he called them the Medicean stars, in Latin, Sidera Medicea. This name wasn't chosen because it described what they were. It was chosen to honor someone. At the time, Galileo was seeking support from powerful patrons. He had just moved from teaching at the University of Padua and was hoping to secure a better position. The Medici family, one of the most powerful families in Italy, ruled Florence and held great influence across Europe. By naming his discovery after them, Galileo hoped to win their favor. In a letter to Cosimo II de' Medici, the Grand Duke of Tuscany, Galileo offered to name the 4 new stars after Cosimo and his brothers. The Medici were pleased, and Galileo was given a position as the court mathematician and philosopher in Florence. In that moment, the moons of Jupiter became tools of influence, wrapped in politics and power. For a while, the name Medicean stars stuck. It appeared in books, letters, and even maps of the heavens. But the name didn't describe what they were. It described who Galileo wanted to impress. Others weren't as eager to use the Medici name. Some astronomers outside of Italy chose different names. Johannes Kepler, the German astronomer and mathematician, had his own ideas. He didn't like the name stars because they clearly weren't stars in the traditional sense. They moved around Jupiter, just like the moon moved around Earth. To him and others, they were moons, satellites. But the word moon wasn't yet used in the way we use it today. At the time, there was only the moon, the one that orbited Earth. The idea that other planets could have their own moons was new and strange, so people argued. In the middle of this, the issue of names kept shifting. While Medicean stars faded slowly, others began to suggest more descriptive names. In 1614, a German astronomer named Simon Marius published a book called Mundus Jovialis, or the Jovian World. In it, he claimed to have discovered the moons of Jupiter at the same time as Galileo. That part was controversial, and Galileo strongly denied it. But what stuck from Marius's work were the names he used. Marius, drawing from classical mythology, named the 4 moons Io, Europa, Ganymede, and Callisto. These were all figures from Greek myth who had been lovers or companions of Zeus, the Greek version of Jupiter. The naming made sense. The moons circled Jupiter, and the names reflected that relationship. According to Marius, he got the idea from Johannes Kepler, who had suggested naming the satellites after Jupiter's mythical entourage. Marius took that suggestion and ran with it. In his writings, he described Io as the closest moon, followed by the others. He even attempted to estimate their distances and orbital times, which were fairly accurate given the tools he had. But Galileo refused to accept Marius's names. He saw Marius as an imitator, someone trying to take credit for his discovery. For years, Galileo's supporters stuck with the term Medicean stars, while others began using the mythological names. It created a divide in the astronomy community. Over time, the Medicean name faded, and Marius's names won out. The logic and consistency of the mythological names were easier to use and understand. They also fit better within the growing system of naming other objects in the solar system. By the 18th and 19th centuries, the names Io, Europa, Ganymede, and Callisto were standard in astronomy books and star charts. But it's important to remember that the name Io didn't originally come from Galileo. It came from a later effort to organize the solar system using stories and symbols from the ancient world. In Greek mythology, Io was a priestess of Hera who caught the eye of Zeus. To hide her from Hera's wrath, Zeus turned her into a cow and sent her wandering the earth, chased by a gadfly. The story is strange and sad, filled with transformation and punishment. It's a myth full of motion and struggle, oddly fitting for a moon that, as we later discovered, is one of the most geologically active bodies in the solar system. The naming journey of Io, from a blank spot in Galileo's notebook to a fiery world with a mythological name, reflects the growth of astronomy itself. In the beginning, names were given for honor and favor. Then they changed to reflect systems and structure. Eventually, they helped frame how we think about celestial bodies, not just as lights in the sky, but as worlds with stories, histories, and forces of their own. The moon, that timed light, how Io helped measure the speed of the universe. By the middle of the 1600s, Io had already helped shift our understanding of the cosmos. No longer just a strange light orbiting Jupiter, it was now accepted as a moon, moving in a pattern that could be tracked and predicted. And it was those patterns, those regular passes behind and in front of Jupiter, that would lead to something no one had yet been able to measure: the speed of light. In 1676, a Danish astronomer named Ole Rømer was living in Paris and working at the Royal Observatory. His job involved improving the accuracy of clocks and making better predictions for eclipses, when one celestial object passes in front of another. One of the best ways to test this was to observe Jupiter's moons, especially Io. Because Io moved quickly around Jupiter and passed into its shadow often, it acted like a tiny repeating clock in the sky. Io orbits Jupiter about once every 42.5 hours. That means roughly every 2 days, it disappears behind the giant planet and then reappears on the other side. For astronomers in the 1600s, this was perfect. Unlike lunar eclipses on Earth, which are rare and hard to predict, Io's eclipses were frequent and regular. You could set a schedule by them. At least, that's what people thought. But Rømer noticed something odd. When Earth was moving toward Jupiter in its orbit, Io's eclipses seemed to happen a little earlier. And when Earth was moving away from Jupiter, those same eclipses happened a little later than they should have. The difference wasn't huge, about 10 to 15 minutes off at most, but it was enough to raise questions. The orbit of Io shouldn't be changing that much. Jupiter's gravity was too strong and too steady. Rømer looked closer. Over time, he compared dozens of Io's eclipses. He wrote down the times, tracked Earth's position in its orbit, and tried to make sense of the changes. Then he came to a bold idea. What if Io wasn't the one changing? What if it was the light itself? At the time, most scientists still believed that light moved instantly. If you lit a lantern or looked at the stars, the light was just there. It didn't have to travel across space. But Rømer's observations didn't fit that idea. The only way to explain the delays was if light had a speed, and if that speed was not infinite. So, Rømer made a simple but clever prediction. He said that as Earth moved farther away from Jupiter, the light from Io's eclipses would take longer to reach us. The farther Earth got, the longer it would take for the light to travel across the growing distance. That meant the eclipses would appear later than expected. Not because Io was late, but because the light from the eclipse took longer to arrive. The opposite would be true when Earth moved closer. Light would arrive sooner, and the eclipses would seem to happen early. In September 1676, Rømer made a public announcement. He said that on November 9th of that year, Io would appear from behind Jupiter about 10 minutes later than expected, based on earlier observations. He was confident that the delay wasn't caused by Jupiter or Io, but by the time light needed to cross the space between the two planets. When November came, he was right. The eclipse happened 10 minutes late, just as he had predicted. It was the first time anyone had used astronomy to show that light had a speed, and that this speed could be measured. Rømer didn't give a precise value for the speed of light in modern units. The tools of the time weren't accurate enough for that. But he did estimate how long it would take light to cross the diameter of Earth's orbit, about 22 minutes according to his numbers. That was very close to the real figure, which we now know is about 16 to 17 minutes for light to travel across Earth's orbit from one side to the other. It was a groundbreaking moment. No one had measured anything like it before, and it was all made possible by Io, by watching its movements, recording its eclipses, and trusting that those movements stayed regular. Io acted like a natural clock, ticking steadily through space. And when the tick seemed late or early, it meant something about the space between us had changed. In later years, other scientists would refine Rømer's work. Dutch physicist Christiaan Huygens used Rømer's timing and some geometry to estimate the speed of light more directly. Others followed, using better instruments and longer baselines. But the foundation was already in place. Rømer had shown that light was not instant, and he had used a small, faraway moon to prove it. It's easy to overlook how powerful that idea was at the time. Until then, no one had thought to use celestial events to probe the laws of nature. But Rømer saw something others didn't. He saw that light could be timed. And by linking that timing to something so regular and dependable, he made the invisible visible. Even more impressive, the work was done without modern clocks, computers, or telescopes like we have today. Everything was done by hand. Rømer used simple timekeeping tools, old-style telescopes, and his own persistence. He had to watch the sky for months at a time, note tiny shifts in Io's appearance, and line those up with Earth's changing position. He took what seemed like a small delay and turned it into one of the most important discoveries in science. The timing of Io's eclipses continued to play a role in astronomy long after Rømer. For a time, they were used as a kind of cosmic clock to measure longitude on Earth. Before accurate clocks were available for ships, some navigators tried to use Jupiter's moons to figure out their position at sea. If you knew when an eclipse of Io was supposed to happen in Paris, and you measured when it actually happened where you were, you could calculate how far west or east you had traveled. It wasn't easy, and the method had limits, but it showed once again how important Io's steady motion could be. Today, we have far more precise ways to measure the speed of light. We use lasers, atomic clocks, and satellites. But none of that would have happened without the first step. A moon orbiting a distant planet, casting its tiny shadow and emerging again like clockwork. A silent flicker. Early observations hinting at a strange world. For a long time after Ole Rømer's discovery, Io remained distant and blurry. Telescopes in the 18th and 19th centuries weren't powerful enough to show any real detail. Astronomers could see Io orbiting Jupiter, slipping behind or in front of the gas giant, but its surface stayed hidden. It wasn't until the 20th century, with the rise of better optics and more advanced techniques, that hints of something strange began to appear. In the early 1900s, a few careful observers began to notice that Io's brightness wasn't always steady. When they pointed their telescopes at the moon, they saw it flicker just slightly. Not enough to draw big conclusions, but enough to raise questions. These weren't the kind of sudden flashes you might expect from an impact or a flare, but slow, subtle shifts. Sometimes Io looked a bit brighter. Other times, it seemed dimmer. The changes didn't line up with Jupiter's shadow or eclipses. They didn't follow any obvious pattern. At the time, no one really knew what to make of it. The brightness shifts were often dismissed as problems with the telescope lens, or changes in Earth's atmosphere. A gust of wind, a thin cloud, or even a small tremor could cause the image to jump or blur. Light from Jupiter itself sometimes spilled over into the image of Io, making it hard to isolate the moon's own glow. With so many ways the image could be distorted, few scientists believed the flickers were coming from Io itself. But as telescope technology improved, the strange changes became harder to ignore. In the 1950s and 1960s, astronomers using photoelectric sensors, devices that could measure brightness more precisely than the human eye, picked up something real, These machines showed that Io's light curve wasn't smooth. It had slight dips and bumps, and sometimes those dips appeared in the same spot in Io's orbit again and again. Some researchers began to suspect that the Moon's surface wasn't uniform. Maybe Io had bright patches, like ice or reflective rock, that caught sunlight at certain angles, or maybe dark areas absorbed more light and caused the drops. The problem was, no one had seen the surface up close. From Earth, even with the best telescopes of the time, Io was still a tiny disk, just a few pixels wide. Then came something more curious. In a few high-contrast photographs taken from observatories in Chile and Hawaii, observers thought they saw a faint blur around Io. It wasn't always there, and it didn't last long. Sometimes, when the Moon passed in front of Jupiter or a background star, there was a slight haze near its edge. It was so faint that many thought it was a trick of light or equipment, just diffraction from the telescope's optics or noise from the film. But there was another possibility, one that only a few dared to consider. What if Io wasn't just reflecting light from the sun? What if something on the Moon, something in its thin atmosphere, was scattering that light? Or what if the Moon was surrounded by some kind of gas or particles, too faint to see most of the time, but visible at just the right angle? That idea didn't have much support. Io was believed to be much like our own Moon, cold, rocky, and mostly dead. No one seriously considered that it might have an active atmosphere, let alone one changing with time. And yet, there were these flickers, these signs that something wasn't quite right. In 1973, just before spacecraft was sent to explore the outer planets, astronomers used new infrared detectors to scan Jupiter's moons. Infrared light, unlike visible light, can pass through dust and gas more easily. It also reveals heat. When they looked at Io, they found warm spots, small but noticeable, on the Moon's surface. Again, this didn't match the picture of a frozen, inactive Moon. If there was heat, there might be geological activity, but the heat was weak, and the instruments weren't sharp enough to say more. One reason these strange hints were often ignored is that planetary science at the time didn't expect small moons to be active. The Moon, Mercury, and Mars all seemed quiet. They had volcanoes, yes, but old ones, frozen in time. There was no reason to think that a tiny moon, smaller than Earth's moon, could still be alive inside. It didn't have enough mass, it shouldn't have enough heat, so whenever something unusual showed up on Io, it was easier to blame the tools than to rethink the assumptions. Even so, a few astronomers began to propose more daring ideas. One of them was that Jupiter's gravity might be pulling and stretching its moons, creating heat through friction inside them. What if Jupiter's pull was kneading Io's interior like soft clay, keeping it hot beneath the surface? If that were true, it could explain the warmth. It could even explain the flickers, if volcanic plumes were rising from the surface and scattering sunlight before fading away. But without close-up photos, it was just a theory. As the 1970s went on, more evidence slowly built up. Radio telescopes began to pick up strange bursts of energy near Jupiter, short, high-frequency signals that seemed to come from the area around Io. Some of these bursts matched Io's position in orbit. Something was interacting with Jupiter's magnetic field in a powerful way. And again, Io was at the center of it. Io was flickering, glowing faintly in infrared, and now causing radio bursts. Something was happening there, something active. But what exactly, no one could say. Even the best photographs showed Io as a blurry sphere, with no clear markings. A few surface features were guessed at. Maybe a crater here, a darker patch there, but nothing solid. Everything changed in 1979 when the Voyager 1 spacecraft reached Jupiter. Its cameras were sharper than anything on Earth. As it flew past Io, it captured the first real images of the Moon's surface, images that shocked everyone. What had once looked like a dead rock turned out to be wildly alive. The surface was covered in strange colors, yellow, red, white, caused by sulfur compounds. There were mountains and plateaus, And in one photo, there was a plume, a volcanic eruption blasting more than 300 kilometers into space. It was the first active volcano ever seen beyond Earth. And suddenly, all the strange flickers, the haze, the warmth, the radio bursts, they all made sense. Io wasn't a cold, quiet moon. It was the most volcanically active body in the solar system. The flickers were the first distant signs of eruptions, of plumes rising and falling, of heat radiating from vents. The haze wasn't a flaw in the telescope. It was gas, thrown into space by violent forces. The strange light curves were caused by shifting materials on the surface, bright new deposits, dark cooling lava, fast-changing terrain. For decades, we had watched Io through a fog of assumptions, thinking it was just another rock in space. But those early hints, dismissed, misunderstood, or ignored, had been trying to tell us something all along. The answer had always been there, flickering in plain sight. Locked in resonance, Io's gravitational dance with Europa and Ganymede. Out in the darkness of Jupiter's system, something remarkable is happening. Io, Europa, and Ganymede are locked together in a constant, repeating rhythm. It's a gravitational arrangement that seems simple at first, but the deeper you look, the more extraordinary it becomes. Io, the closest of the three, takes about 1.77 days to orbit Jupiter. Europa, the next moon out, takes just about twice that, 3.55 days. And Ganymede, the largest moon in the solar system, orbits in about 7.15 days, almost exactly 4 times as long as Io. That timing isn't a coincidence. It's a pattern, a mathematical lock. For every orbit Ganymede completes, Europa orbits twice, and Io goes around 4 times. This is called a 1, 2, 4 resonance. Each moon's gravity affects the others. As they orbit, they don't just follow Jupiter's pull, they also tug on one another. These pulls are tiny, but they add up over time. They create a kind of ongoing conversation between the moons. It's a rhythm that never breaks, always snapping back into place. Imagine a dance where 3 people always end up in the same positions after a set number of steps. Even if one of them moves slightly too fast or slow, the others adjust to pull it back into sync. That's what happens with these moons. If one moon drifts even slightly out of rhythm, the gravitational tugs from the others gently correct it. This resonance isn't fragile, it's stable. In fact, it's so stable that it may have lasted for billions of years. The resonance changes the shape of the moon's orbits, especially Io's. If there were no other moons around, Io might settle into a perfect circle around Jupiter. Over time, tidal forces, those slow, stretching pulls, tend to round out orbits. But because of the resonance, Io's orbit stays a little stretched or elliptical. Every time Io passes Europa, and every second pass of Europa when it lines up with Ganymede, it gets a small gravitational nudge. These regular nudges stop the orbit from becoming perfectly round. This slightly stretched orbit may not sound like much, but it's the key to something much bigger. As Io moves around Jupiter in this oval-shaped path, it speeds up when it's closer to the planet and slows down when it's farther away. Jupiter's huge gravity pulls harder when Io is closer, and less when it's farther. This changing force squeezes and stretches Io again and again. Think of it like squeezing a rubber ball in your hands, over and over. That motion creates heat inside the ball. For Io, the same thing happens, except it's not from your hands, it's from gravity. The constant flexing of Io's interior creates friction, and that friction creates heat, a lot of it. So much, in fact, that it powers the most violent volcanic activity we know of. Without the resonance, Io might be just another cold, rocky moon. But because it's trapped in this 3-way dance with Europa and Ganymede, its orbit stays just uneven enough to keep the heat flowing. And it's not just heat. The movement of molten material inside Io likely helps shape its strange, ever-changing surface. Lava lakes, tall mountains, and massive plumes of sulfur erupting into space. Every time Io completes an orbit, it lines up with Europa in a slightly different place. The same happens between Europa and Ganymede. Over time, these alignments repeat in a cycle, roughly every 7 days. It's like clockwork. These alignments cause the moons to tug on each other in a way that reinforces the pattern rather than breaking it. In many orbital systems, small changes or tugs can build up and cause chaos over long timescales. Orbits can become unstable, drifting apart or spiraling in. But the 1, 2, 4 resonance among Io, Europa and Ganymede acts like a self-correcting system. If one moon begins to drift, the gravitational tugs pull it back into place. It's not perfect, but it resists change in a way that few other systems do. This stability may have allowed the moons to evolve in very different ways. Ganymede, farther out, is large and icy, with signs of past tectonic activity. Europa, in the middle, is covered with a shell of ice and likely hides a subsurface ocean, kept warm by the same tidal heating that drives Io's volcanoes. Io, being closest to Jupiter, feels the strongest pull and the most intense heating. The result is a fiery surface unlike anything else in the solar system. It's no accident that these 3 moons are so different. Their shared resonance ties them together, but each moon experiences that gravitational rhythm in its own way. Io bears the brunt of it, constantly flexed and heated. Europa gets enough warmth to keep an ocean beneath its crust. Ganymede, farther out, gets less tidal heating, but still feels the slow, steady push of the resonance. Scientists believe the resonance likely built up slowly over time. As the moons formed and moved outward due to tidal interactions with Jupiter, their orbital periods began to line up. One capture led to another. Io and Europa likely locked into a 2, 1 resonance first, and later Europa was pulled into a 2, 1 resonance with Ganymede. The full 1, 2, 4 pattern followed. Once established, the system became held in place by the same gravity that created it. The resonance also helps keep the system from falling apart. Without it, the moons might slowly drift into new positions, or even crash into one another over long timescales. The pattern acts like a kind of protection. It prevents chaos. There are other examples of resonances in the solar system. Pluto and Neptune are in a 3, 2 resonance, and Saturn's moons also show similar patterns. But the one between Io, Europa and Ganymede is the most famous and the most powerful. It's one of the few places where the effects of resonance are not only visible, but extreme. On Io, those effects have carved a world of fire from the cold rock of space. The invisible chains, how Jupiter's magnetosphere sculpts Io's orbit. Out in the Jovian system, gravity isn't the only force pulling on Io. There's something else, invisible, but no less powerful. Around Jupiter stretches one of the largest magnetic fields in the solar system. It extends for millions of kilometers in every direction, dwarfing the planet itself. And Io, trapped within it, is not just orbiting under gravity's control. This magnetic field, or magnetosphere, is created by Jupiter's fast rotation and its metallic hydrogen interior. The planet spins once every 10 hours, which is incredibly fast for its size. That spin turns Jupiter into a kind of giant dynamo, a magnetic engine that generates a field so wide it can reach past Saturn's orbit when stretched by the solar wind. Inside this field, charged particles are trapped and whipped around the planet at incredible speeds. These particles form a kind of plasma disk, dense, hot, and always moving. And Io, orbiting right through this disk, is constantly exposed to its effects. Io isn't just passing through empty space, it's moving through a sea of charged particles. These particles hit Io like a wind, except it's not made of air, but ions and electrons. As Io travels through this magnetic environment, it experiences a kind of electrical drag. Think of it like pushing a metal object through a magnetic field. Resistance builds, currents form, something pushes back. Because Io has an atmosphere, and because that atmosphere becomes partially ionized by sunlight and by particles from Jupiter's magnetosphere, electrical currents can flow through it. As Io moves through Jupiter's magnetic field, it acts almost like the wire in a generator. The motion across the field lines creates a voltage. That voltage drives a flow of electricity through Io's atmosphere and into the surrounding space. The result is what scientists call the Io flux tube, a channel of electric current connecting Io to Jupiter. It's like a glowing, invisible cord. Charged particles flow along magnetic field lines between the two worlds, lighting up the planet's upper atmosphere near the poles. When spacecraft like Galileo and Juno flew past Jupiter, they saw these glowing spots, bright auroras, triggered not by the sun, but by Io's presence in the field. But these currents aren't just lighting up Jupiter, they're also pushing back on Io. The moving currents in Io's atmosphere create magnetic fields of their own. These fields interact with Jupiter's magnetic field. The effect is small but constant. It's like a magnetic brake, a force that resists Io's motion through space. Over long timescales, this braking effect can alter the orbit. It can slow down the Moon's rotation slightly, or cause its orbit to drift in tiny ways. These changes don't happen overnight. They take millions of years. But over those long stretches of time, the magnetic forces can adjust the shape of Io's orbit, even as gravity from the resonance tries to keep it locked. It's a quiet struggle. Gravity pulling one way, magnetism pulling another. Most of the time, gravity wins. But electromagnetism also never stops pushing. What's even stranger is that Io may also be charging and discharging in cycles. As it moves through Jupiter's magnetic field, parts of its surface can build up electric charge. That charge doesn't stay still. It shifts, builds, and sometimes jumps. Lightning-like discharges might crackle across Io's upper atmosphere, unseen by human eyes, but sensed by instruments on passing spacecraft. These discharges can affect the Moon's atmosphere, creating pulses of heat, and sometimes changing the way particles escape into space. Io's interaction with Jupiter's magnetosphere also creates a kind of electromagnetic wake behind it, a turbulent region where particles are stirred and twisted. As Io moves forward, it leaves behind a disturbed region of space that slowly settles. These ripples don't affect the orbit directly, but they show how deeply the Moon is tied to its environment. All this electromagnetic activity also affects Io's atmosphere itself. The intense radiation from Jupiter's field can strip particles away, especially during times of increased solar activity. Sulfur and oxygen atoms, blasted out by volcanoes on Io's surface, can be ionized and swept into Jupiter's magnetic field. Once inside that field, they spiral along the magnetic lines, creating donut-shaped rings of plasma that encircle the planet. These plasma rings are enormous and contain many tons of material. Much of that material originally came from Io. As the Moon loses mass to Jupiter's field, it contributes to the larger magnetic system. But this process varies depending on Io's volcanic activity, the position of the Sun, and even fluctuations in Jupiter's magnetic output. The result is a feedback loop. Io's volcanoes feed the magnetosphere, and the magnetosphere in turn shapes Io's motion and surface conditions. Even Io's day-to-day motion is affected. Because it travels through a rotating magnetic field, Io feels something like a torque, a twisting force. Jupiter's field rotates once every 10 hours, but Io orbits every 1.77 days. That mismatch creates friction. The difference between Io's motion and the magnetic rotation speed causes currents to surge across the Moon's surface and atmosphere. The twisting doesn't pull hard, but it never stops. Over time, this twisting may influence how fast Io spins. While Io is currently tidally locked, always showing the same face to Jupiter, it wasn't always that way. Long ago, when the Moon first formed, it likely rotated more freely. The combined pull of gravity and magnetic drag eventually forced it into this locked state. Now, even though it stays facing Jupiter, the tug of the magnetic field continues to press against it, always trying to adjust its balance. Scientists studying Io's orbit over long timescales have to factor all of this in. The gravitational resonance gives us a clear framework for understanding Io's path. But the electromagnetic effects are like small corrections, fine-tuning the orbit in ways we're only beginning to measure. These effects are harder to observe directly, but they show up in small changes. In the timing of Io's orbit, in the shifting patterns of auroras on Jupiter, and in the behavior of the plasma torus that circles the planet. To detect these small changes, scientists use spacecraft like Juno, along with Earth-based telescopes that can track Io's position down to fractions of a second. By comparing these measurements over decades, researchers can look for signs that the orbit is drifting, wobbling, or changing shape. And while gravity explains most of what we see, some of the leftovers, the odd fluctuations, may be the work of Jupiter's invisible chains. It's a reminder that space isn't empty. Even in the vacuum between Jupiter and its moons, fields and forces are at play. Magnetic lines stretch and snap. Charged particles race across the system like wind in a storm. This complex interaction gives Io a kind of dual identity. It's both a moon and a conductor. The result is a dance of energy, electricity, and magnetic pressure. Io doesn't just orbit, it shapes the space around it, and in turn is shaped by it. Even if we could turn off the gravity for a moment, erase the pull of Jupiter and the other moons, Io would still feel the touch of the magnetic field. It would still spark and surge and resist. The orbit might drift. But for a little while, the memory of those invisible chains would remain, written into every particle of the moon's motion, as if Jupiter's magnetosphere had left its signature behind. Volcano-fueled plasma, the strange torus encircling Jupiter. Io's plasma torus is a loop of sulfur, oxygen, and sodium ions, material that started out as solid rock on Io's surface but was blown high into space by volcanoes. These gases spread out into space, and once they leave the surface, they begin a transformation. They get zapped by sunlight and struck by high-energy particles in Jupiter's magnetosphere. Electrons knock off atoms, and the gas becomes ionized, turning into plasma. Plasma is different from normal gas. It's made of charged particles, positive ions, and free electrons. Once a gas becomes plasma, it starts behaving in new ways. It can carry electric currents. It can be trapped by magnetic fields. And near Jupiter, those magnetic fields are strong enough to hold the plasma in the shape of a torus, a fat ring centered around the planet's magnetic equator. The torus stretches from about the orbit of Io and out beyond it. It's hundreds of thousands of kilometers wide. And even though it's spread out and thin compared to an atmosphere, the torus holds a massive amount of energy. It glows in ultraviolet light. It pulses and flickers with changing currents. And it rotates with Jupiter's magnetic field, sweeping around the planet every 10 hours. This constant motion means the plasma is racing around faster than Io orbits. The torus overtakes Io again and again, dragging across its thin atmosphere, feeding more particles into the mix. It's a feedback loop. Volcanoes release gas, gas escapes into space, it becomes plasma, the plasma joins the torus, and the torus circles back to brush against Io again, pulling more material out. Each loop builds the torus stronger. The main ingredients of the torus are sulfur and oxygen. These elements come from the sulfur dioxide that dominates Io's volcanic emissions. When a volcano erupts on Io, it shoots plumes of sulfur dioxide gas miles into the sky. Some of this gas freezes and falls back as frost, but some of it escapes entirely. Once in space, it gets broken apart by sunlight and radiation. Sulfur atoms and oxygen atoms are left behind. Those atoms don't stay neutral for long. High-energy electrons strike them and turn them into ions. Sodium is another piece of the puzzle. It's not as common as sulfur, but it plays an important role in the plasma dynamics. Once ionized, they glow with a distinctive yellow color. In fact, sodium emissions from the torus were among the first things scientists detected from Earth-based telescopes. When Io has a major eruption, scientists can sometimes see the torus brighten or shift in response. A single eruption on the surface of a distant moon can change the shape of a plasma ring stretching millions of kilometers through space. No other moon in the solar system changes its planet's magnetic surroundings so directly. The material blown off Io becomes part of Jupiter's magnetic system. The planet captures it, wraps it, and spins it into a ring of power. Inside the torus, the density and temperature vary. Closer to Jupiter, particles are more energetic. Farther out, the plasma thins and cools, but the whole structure is dynamic. It breathes, it pulses, sometimes it expands. Sometimes it collapses slightly. Scientists measure the torus using spacecraft and ultraviolet telescopes. They track changes in brightness, movement of ions and radio waves coming from the system. Earth-based observatories, using powerful spectrographs, have tracked the torus from afar. These tools let scientists see specific wavelengths of light emitted by sulfur and oxygen ions, giving clues about the plasma's energy and movement. There's also something called the plasma interchange instability. This is a process that stirs the torus like a spoon in soup. Inside the torus, denser and hotter plasma wants to move outward. Cooler, less dense plasma from the outer edge wants to move inward. The result is a slow but constant mixing of materials. This motion helps keep the torus energized and balanced. The energy from the torus doesn't stay in the torus either. Some of it gets funneled along Jupiter's magnetic field lines and into the planet's poles. There, it lights up the atmosphere with auroras. These aren't like Earth's green northern lights. Jupiter's auroras are brighter, faster, and more intense. They're partly powered by the plasma torus. And sometimes, you can even see footprints of Io in the aurora, bright spots where the magnetic connection between Io and Jupiter touches the atmosphere. The torus is also leaking. Not all the plasma stays in the ring. Some of it drifts outward into Jupiter's outer magnetosphere. Some of it gets swept away by the solar wind. Over time, this outflow creates a long tail behind Jupiter, stretching millions of kilometers into space. It's like a trail of breadcrumbs, marking where particles from Io have gone. Instruments on spacecraft passing through this tail have found traces of sulfur and sodium, confirming that Io's influence reaches far beyond its orbit. Volcanic eruptions, usually thought of as ground-level events, become drivers of space weather. A mountain exploding on a moon changes the radiation belts of a planet. It's a bridge between worlds that seems hard to imagine, yet it's happening every day. The exact details of how ions are accelerated, how energy is transferred, and how the torus responds to small changes in Io's activity are ongoing areas of study. Recent missions have helped answer some questions, but they've also raised new ones. Over time, scientists hope to get even better views of the torus, possibly with new probes that could fly through it again, taking direct measurements. A world without craters, why Io's surface never ages. If you look at the surfaces of most moons in the solar system, you'll see scars. Craters, dents and deep gouges left by billions of years of impacts. These marks stay in place because there's no wind, no rain, and usually no geological activity to erase them. On some moons, a single crater can last longer than life has existed on Earth. But Io is different. When spacecraft first sent back images of Io, scientists were surprised. They expected a pockmarked world. Instead, they got smooth areas, oddly shaped mountains, and colorful patterns of yellows, reds, and whites. Most importantly, there were almost no craters. For a world as old as Io, this was strange. It wasn't because Io had somehow avoided being hit by space rocks. Every moon near Jupiter gets bombarded over time. Jupiter's gravity pulls in asteroids and comets, increasing the chance of impacts. So Io has definitely been hit many times, but where are the craters? The answer is that they're gone. Or rather, they're buried, hidden under fresh lava, coated in sulfur, or covered by deposits from eruptions. On Io, the surface never stays the same for long. Volcanic activity is so frequent and widespread that any crater gets erased in a short span of time. In cosmic terms, it's almost instant. On icy moons like Europa, Ganymede, or Callisto, things are mostly quiet. They have icy shells, and while some of them may have internal oceans or slow-moving ice flows, their surfaces barely change over millions of years. That's why their craters last. A crater on Callisto might have been there for 4 billion years and still looks the same. But on Io, change is the rule. Its volcanoes are not small hills with slow lava trickles. They're massive, violent, and constantly reshaping the surface. Some eruptions cover areas the size of Texas. Some send plumes hundreds of kilometers into space. When a volcano erupts on Io, it can completely remake the landscape. Even between major eruptions, small ones are happening all the time. Lava oozes from cracks, creating new flows. Sulfur dioxide vents spray out gas and frost. Over time, these deposits stack up and spread out. This constant resurfacing means that anything old, like an impact crater, gets smoothed over or filled in. Some regions of Io are coated with bright sulfur, while others show darker basalt-like lava. The color patches give clues about the temperature and age of the surface. Brighter areas tend to be colder, dusted with sulfur frost. Darker areas are warmer and usually fresher, where lava has recently flowed. These darker patches are often located around volcanic vents, suggesting recent or even ongoing activity. There are places on Io where lava flows are stacked in layers, one on top of another. These are areas where eruptions have occurred again and again in the same location. Over time, the old surface gets buried under multiple new layers, sometimes several kilometers thick. This shows just how fast and deep the process of resurfacing can be. Because of this non-stop activity, Io's surface is considered extremely young. Scientists estimate the average surface age of Io is less than 1 million years old, possibly much younger in many regions. That means that across the entire Moon, almost every area you see today has been reshaped or renewed in recent geologic history. This has made Io both a mystery and a challenge for scientists. With no craters to study, it's harder to trace the Moon's older history. On other moons, the number and type of craters can give clues about the Moon's age, the nature of impacts, and even the conditions in the early solar system. But on Io, that record has been wiped clean. Instead of reading history in craters, scientists study Io's volcanoes, lava fields, and the changing surface patterns over time. Comparing images taken years apart, they can see how features grow, fade, or move. Some volcanic pits change shape between observations. Some disappear altogether, replaced by new flows. In this way, Io becomes a living world, changing fast enough to watch it happen. The lack of craters also changes how heat spreads through Io. On cratered worlds, the surface is rough, with deep depressions that can trap cold. On Io, the fresh, flat lava fields radiate heat more evenly. Some of these lava fields glow in infrared, showing they're still warm long after the eruption ends. Instruments have measured temperatures on these flows far above what would be expected for a moon that size. This heat is not from sunlight, it comes from within. Io's volcanic heat comes from tidal forces, as Jupiter's massive gravity flexes the moon like a rubber ball. But the effects are visible on the surface. The heat causes lava to rise, crusts to crack, and new material to pour out. And with every eruption, a bit more of the surface is renewed. Some of Io's features do last a little longer. Tall mountains, for example, may stay in place for a while, especially if they're made of harder rock. These mountains don't seem to be volcanic, but rather built by tectonic forces, sections of crust pushed together. Some rise higher than Mount Everest, but even these giants don't stay unchanged. Lava flows often creep up their sides, and deposits from plumes can coat their peaks. Over time, even the mountains are slowly covered. The idea of a world without craters means scientists can study a living surface, one that tells us not about the deep past, but about the present and near future. Io's lack of craters isn't a sign of peace, it's a sign of constant upheaval. Frozen sulfur snowfields and lava lakes, a patchwork of extremes. The bright regions on Io are coated in sulfur dioxide frost. This frost forms when gas from volcanic vents freezes as it spreads out and settles on the surface. The sunlight bouncing off these frozen fields gives them a brilliant white or pale yellow color. From orbit, they almost look like snow, but this snow is not water, it's frozen gas, fragile and thin, coating the land like frost on a window. Temperatures in these regions can drop far below freezing. In fact, some parts of Io's plains are among the coldest surfaces ever measured in the solar system. At night, without the sun, the surface chills quickly. The frozen sulfur becomes stiff and brittle. These areas look calm and still, but they are always at risk of changing. One eruption, even far away, can throw heat or ash across these plains and remake them in a moment. Then there are the dark areas. These are pits and flows where lava has surfaced. The lava on Io is extremely hot, hotter than any lava on Earth. In some places, it forms lakes that stretch for tens of kilometers. These lava lakes are not fully solid. They bubble, crack, and shift, with liquid rock rising and falling in cycles. The crust on top might cool and harden for a while, then suddenly break open, letting more lava spill out. The surface of these lakes is often dark grey, black, or deep red, depending on how fresh and hot the lava is. One of the most famous of these lava lakes is Loki Patera. It's larger than Lake Ontario and is shaped like a massive horseshoe. Scientists think the crust of Loki Patera slowly cools and thickens, then collapses in large sections, like ice breaking on a frozen pond. These collapses create brightening events that are visible even from Earth, and they happen regularly. Elsewhere on Io, there are other lava lakes and open flows. Some form in volcanic pits known as paterae. These are deep, irregular depressions where eruptions have occurred again and again, carving out huge basins. Some paterae are ringed by tall cliffs, and their floors may hold pools of molten rock or cooling flows in twisted shapes. Between these extremes, frozen plains and lava lakes, lie transition zones. These areas are especially rich in detail. A plume from a nearby volcano might spray ash across a cold surface, creating streaks and patterns that stretch for hundreds of kilometers. The ash can color the land in red, orange, or even greenish tints, depending on its sulfur content. These streaks tell a story about wind direction, eruption power, and how quickly heat spreads across Io's surface. In some places, you can move just a few kilometers and go from an icy landscape to one that could melt rock. This creates tension on the surface. As lava spreads, it meets frozen sulfur and causes violent reactions. The heat can make the sulfur flash into gas, creating pressure and even small explosions. From space, Io doesn't look like a familiar moon or planet. It has no blue oceans, no green forests, no smooth grey plains. Instead, it shows off swirling patterns of red and yellow, with sharp patches of black and white. This variety helps scientists track change. Over time, they watch how lava lakes grow and shrink, how frost plains darken or brighten, and how new eruptions add new pieces to the patchwork. Changes in color, shape, or brightness tell researchers where heat is rising, where gas is venting, and where the next eruption might occur. Certain volcanoes, like Loki Patera, follow cycles that scientists can study. Others appear with little warning, erupting suddenly and throwing lava across previously cold areas. These surprise events can create entire new lava fields within days. In some cases, they bury old features and make the surface look completely different from one year to the next. Because of this constant change, there are few places on Io that stay the same for long. Even the frozen sulfur plains can disappear quickly if lava flows nearby. And even lava lakes don't stay active forever. Some cool down and crust over, becoming dark patches where heat still lingers underneath. Others reactivate, glowing bright in infrared and erupting again after years of silence. The atmosphere that collapses every night. Io's atmosphere is so thin that if you stood on the surface, you wouldn't feel any pressure at all. There's no wind to push your skin, no sky to scatter light, and no clouds to block the sun. You could walk across Io's surface, and unless you had special equipment to measure it, you might never know an atmosphere was even there. The main gas in Io's atmosphere is sulfur dioxide, or SO2. On Earth, this gas is a minor pollutant, something you smell near volcanoes or in burning fossil fuels. On Io, it's everywhere. Volcanoes throw it into the sky in massive plumes. Surface frost made of frozen SO2 gives off gas when warmed by sunlight. For a few hours each day, as Io turns and faces the sun, that gas builds into a thin veil across the moon's surface. But this atmosphere doesn't last. As the sun sets on Io, the temperature plummets. Without sunlight, the surface cools rapidly. And when that happens, the atmosphere begins to fall. The sulfur dioxide gas doesn't just thin out, it freezes. The entire atmosphere collapses. This happens every single night on Io. Sulfur dioxide, which can exist as a gas when the surface is warm, begins to condense when temperatures fall. In Earth terms, it's a bit like fog turning into frost, but on a much more dramatic scale. Across the night side of the Moon, the SO2 gas turns into tiny crystals and drops down to the surface, forming a thin layer of frost. Scientists call this atmospheric collapse, and Io is one of the few places where we've seen it happen so regularly and completely. There's no weather in the usual sense, just this repeating cycle of gas rising and falling, driven only by sunlight. When Io rotates into daylight, the frost begins to heat up. And just like that, it starts to vanish again, sublimating straight back into gas. There's no liquid stage in between. The frost goes directly from solid to vapor, reforming a temporary atmosphere that only lasts as long as the sun is shining. This process drives enormous pressure swings. Even though Io's atmosphere is already thin, only a billionth the pressure of Earth's, it becomes even thinner at night. Daytime pressure is up to 10 times higher than at night. On a world with a thicker atmosphere, that kind of swing would bring storms and wind. On Io, it simply means the atmosphere appears and disappears every 42 hours, which is how long a day is on the Moon. From orbit, spacecraft can actually measure this change. Instruments that look at how light moves through Io's atmosphere see a clear pattern. When the Moon is in sunlight, sulfur dioxide gas shows up in the data. When Io moves into Jupiter's shadow, the gas vanishes. Unlike planets with thick atmospheres that hold heat, Io responds almost instantly to light and dark. When the sunlight fades, the gas freezes. When it returns, the frost vanishes. There's almost no delay. That means the air on Io doesn't behave like air at all. It behaves more like steam, rising when warm, disappearing when cold, and constantly switching back and forth. On one side of the Moon, gas rises from the surface. On the other side, gas is falling and freezing. At the dividing line, what we'd call the terminator between day and night, the changes are rapid. You can imagine a kind of invisible tide of gas moving around the Moon as it turns. Over time, areas that stay cold tend to build up thicker deposits. Warmer areas near volcanoes might never allow frost to settle at all. In between, you get a kind of map, zones where the SO2 atmosphere gathers and zones where it disappears. Every time a volcano erupts, it throws more sulfur dioxide into the sky. That gas might build up an extra thick patch of atmosphere for a while, especially if the eruption happens near the day side. But if it happens at night, most of that gas won't last. It will freeze out almost immediately, so even the timing of volcanic activity matters. A blast at noon can fill the sky. A blast at midnight just adds frost. Over time, this constant freezing and thawing leaves its mark. Some scientists believe it shapes the surface in subtle ways. Frost builds up in layers. As it sublimates, it may carry away fine dust or sulfur particles. This slow erosion, over hundreds or thousands of cycles, could be one way Io's plains stay so clean and bright in appearance. It's like a natural surface cleaning system, powered entirely by sunlight and freezing temperatures. On Earth, the atmosphere shifts a bit, changes temperature, changes density, but it's always there. On Mars, the thin air also stays in place, even if it gets cold. But on Io, it's all or nothing. Air becomes frost. Frost becomes air. It's a reminder that not all atmospheres are stable. Io's atmosphere lives a short life each day, born at sunrise and gone by sunset. It's more like a breath, tied directly to the turning of the world. Peeling back the layers, what Io's shape tells us about its core. Every large world in the solar system takes on a shape that reflects what's happening inside. For planets and moons that spin, like Io, this usually means a bulge at the equator. The spinning motion creates a force that pushes outwards, and over time this causes the equator to rise a little higher than the poles. Earth has this bulge, so does Jupiter. Io is no different, but its shape isn't just a product of spin. It's also shaped by gravity, heat, and internal structure. Spacecraft flying past Io have helped us map its size and shape with great care. There's a slight flattening at the poles, and a small but measurable bulge at the equator. This is exactly what we'd expect from a spinning body. But the details go deeper than that. The way Io bulges, or doesn't bulge, gives clues to how stiff or flexible the material inside is. And that depends on what it's made of, and how it's layered. One key number scientists look at is called the second-degree gravitational harmonic. It's a measure of how gravity is distributed around the body. If a moon like Io has more mass closer to the center, its gravity will behave differently than if it's more spread out. By combining gravity data from spacecraft with visible shape measurements, scientists can work backward to create models of what Io must be like inside. These models suggest that Io has a layered structure and possibly even a molten or partially molten core. The outer shell, what we see as the surface, is made of solid rock and sulfur-rich deposits. Beneath that is likely a thick mantle, where much of the tidal heating from Jupiter is turned into energy. And below that, at the center, could be a dense core made of iron or iron-sulfur mixture. None of this has been directly seen. It was all inferred from measurements of Io's overall shape and how it responds to Jupiter's pull. For example, if Io's core were solid and made of dense metal, the Moon would behave slightly differently than if the core were molten. It would wobble less. Its surface might bulge in other places, and the way the surface rises and falls as Io orbits would also change. These subtle behaviors help refine what kind of core Io has. Scientists also consider tidal deformation, how Io stretches as it moves around Jupiter. Jupiter's gravity pulls harder at some times than others. This constant squeezing and relaxing causes the Moon to flex. That flexing powers Io's volcanoes. But how much heat is produced depends on how the interior is layered. If the core were solid and stiff, much of the tidal energy would be lost or turned into vibrations. But if the mantle is soft, or if the core is liquid, it can absorb and store that energy more efficiently. This creates more heating and more volcanic activity. The shape of Io, how it bulges, how it flattens, and how it moves, tells scientists which models make sense and which don't. Over time, the measurements start to rule out certain possibilities and point towards others. One of the more surprising findings is just how tightly connected Io's outer appearance is to its inner structure. Even small irregularities on the surface can reflect what's going on deep below. For instance, Io has some regions that are slightly higher or lower than others. These surface elevations, when compared to gravity measurements, suggest underlying variations in density. In some places, the crust may be thicker. In others, the mantle may rise closer to the surface. This kind of mapping helps scientists guess where magma might be more likely to break through and erupt. There's also evidence that the shape of Io is being slowly changed over time. Some parts of the surface may be slowly rising or sinking. These changes are tiny, measured in meters, not kilometers, but they matter. They affect how the shape is measured, and that in turn affects how the interior is modeled. Io's gravitational pull on Europa and Ganymede can change their orbits, but the reverse is true too. The way Io is tugged and pulled by these nearby moons affects its shape. If Io had a soft or fluid core, it would respond more dramatically to these outside influences. That responsiveness shows up in tracking data and orbital models. A world with a solid, evenly layered interior will spin steadily. But if different parts of the interior rotate at slightly different speeds, a possibility if the core is liquid or partially molten, then that can affect the Moon's spin over time. A non-uniform interior can create small but measurable shifts in the way the Moon turns. No single measurement is enough, but when combined, Io's shape, gravity field, orbital behavior, rotation rate and surface changes, they tell a story of a layered, heated and dynamic Moon with a complex interior. No drills were needed, no landers had to dig into the crust. Instead, by watching how Io moves, how it sits in space, and how it responds to the forces around it, scientists were able to peel back the layers of this world. And what they found was just as strange and just as fascinating as the eruptions that light up its surface. The mantle in motion, unlike the iron core, which sits deep in the center and may be molten, The mantle is made mostly of silicate rock. On most rocky bodies, including Earth, the mantle is mostly solid, but can move very slowly over time. On Io, though, the is constantly being stretched and squeezed. Inside the mantle, the rock doesn't stay rigid. The pressure and heat from tidal flexing cause parts of it to soften and begin to melt. Not entirely. It's not like an ocean of magma sloshing around. But enough of the rock becomes partially molten, like thick syrup or soft taffy, to allow it to move in complex ways. Scientists describe this as a magma-rich mantle, where small pockets of melted rock are mixed in with more solid material. As Jupiter's gravity tugs on Io, these molten parts get stirred. The flexing motion pushes hot material toward the surface and pulls cooler material down. This doesn't happen in a neat circular loop. It's more chaotic, like a blender without a lid. The entire mantle layer is in motion, stirred by the rhythm of Io's orbit. This motion keeps the heat from staying in one place. It spreads it out across the interior, helping explain why volcanic activity can pop up almost anywhere on the surface. Scientists use computer models to simulate this kind of motion. They feed in numbers for the strength of the tidal forces, the likely temperatures, and the thickness of the crust. Then they watch how the simulated mantle behaves over time. The models show that the most active heating happens not at the core or the surface, but right in the middle, the silicate mantle. That's where the energy gets trapped and transformed, powering the eruptions we see on the outside. The more molten the mantle is, the more it can move, and the more it moves, the more it generates heat. It becomes a feedback loop. But there's a balance. If the mantle gets too hot and too molten, it starts to behave like a liquid, and it can't hold shape well. That changes how Io reacts to Jupiter's pull. So there's a sweet spot, part molten, part solid, that allows for maximum tidal heating. Scientists think Io is sitting right in that zone. Just like Earth's mantle has areas that are hotter or cooler, Io's mantle may have spots where melting is more advanced. These zones might feed specific volcanoes or cause certain regions of the surface to shift more than others. The idea of a mantle plume, a rising column of hot rock pushing toward the crust, has been used to explain how some of the largest volcanoes on Io stay active for years at a time. Unlike the cores of gas giants or the icy mantles of outer moons, Io's mantle is made almost entirely of rocky material, mostly silicates like olivine and pyroxene. These minerals have melting points that make them ideal for this kind of slow-motion heating. They don't melt too easily, so the mantle doesn't become fully liquid. But they do soften enough to allow movement. The partially molten mantle makes the entire moon a bit more flexible. It doesn't behave like a solid stone. Instead, it squishes and deforms slightly as it moves through its orbit. That deformability tells scientists the mantle isn't just hot, it's in motion. By measuring how much Io flexes, they can estimate how soft the mantle is, how deep the melting goes, and even how fast the material inside is flowing. The Galileo spacecraft saw active volcanoes at many different longitudes and latitudes. No single spot was always quiet. That widespread of activity supports the idea of a mantle in motion, with no fixed hot zones or cold zones. Instead, the whole mantle behaves like a stirred pot, where heat can pop up almost anywhere. Other moons, like Earth's moon or even Mars, have cooled down over billions of years. Their interiors froze and their surfaces became quiet. But Io is being reheated constantly from the inside. Gravitational energy turns into friction, and friction into heat. And that soft, moving mantle is what feeds the lava lakes, the fountains of sulfur, and the rivers of molten rock that streak across the surface. It's what allows a world without plate tectonics, without oceans, and without a thick atmosphere to be so geologically active. Cracking the shell, signs of subsurface intrusions beneath volcanoes. Volcanoes like Loki Patera and Pele erupt with tremendous energy, but the magma they release doesn't come straight from the core or even the deep mantle. Instead, there's growing evidence that Io has a shallow and complex system of magma reservoirs and underground channels, features that act as a kind of local plumbing. directing molten material to the surface. This network is not visible with the naked eye, but by watching how and where eruptions happen, and by tracking how lava flows and resurfaces, we can start to guess at what's happening just beneath the shell. Some of the best clues come from infrared images taken during flybys, and these images show not just where lava is visible, but how temperatures change over time. When a volcano suddenly heats up, or when a lava lake grows in size, it suggests that something has moved underneath. Magma has intruded into a shallow chamber. These shallow intrusions don't always erupt. Sometimes magma pushes into the crust and stays there. The crust cracks and lifts slightly like dough swelling under heat. But instead of breaking through the surface, the molten rock freezes in place, forming a horizontal or vertical body of solidified magma beneath the shell. Scientists call these features dikes when the magma moves upward, slicing through layers of crust, or sills when it spreads sideways between them. On Earth, similar formations are found all over ancient volcanic regions. On Io, the heat signatures and repeated resurfacing suggest dikes are a common feature. When magma forces its way upward, it cracks the brittle crust. These cracks, once formed, can become recurring pathways for future eruptions. A single dike intrusion might last hours or days, slowly moving magma toward a vent. Or it might feed a more sudden and violent eruption if the crust above gives way all at once. The most powerful eruptions on Io likely begin this way. Pressure builds in a shallow magma pocket. Eventually, the overlying crust can no longer contain it. The crust fractures, and lava erupts through new or existing vents, sometimes with explosive force. These eruptions can coat hundreds of square kilometers in fresh material. Some of the observations that support this model come from repeat flybys of the same location. Take Loki Patera, for example. When the surface cools and hardens, it looks dark. Then, in regular intervals, a wave of fresh lava sweeps across it, lighting it up again in infrared. That wave is thought to come from a sudden overturning of lava, but before that happens, magma likely builds in a reservoir just below. A dike or channel connects this pocket to the lake floor, and once the pressure is high enough, the whole surface breaks open. Other volcanoes seem to erupt more like fountains or plumes. These may be fed by vertical dikes that rise quickly through the crust. The speed and shape of the eruption depends on how narrow or wide the dike is and how much gas is mixed in with the magma. There are even signs that dikes may influence the shape of the crust over time. Repeated intrusions in the same area could create swelling, faults, or even collapse pits as the crust shifts and adjusts. Galileo images showed strange depressions and ridges near many of Io's volcanoes. Some of these features line up with places that have seen multiple eruptions, suggesting the underground plumbing system has reshaped the landscape in lasting ways. The energy that powers these shallow movements still comes from deep tidal heating in the mantle, but the way that energy reaches the surface depends on these intermediate steps. A hot, flexible mantle sends molten rock upward. As it rises, it gathers in pockets or squeezes into cracks. Some of those cracks widen and rise toward the surface, forming dikes. Others spread sideways or feed into reservoirs under calderas and lava lakes. Modeling these subsurface structures isn't easy. Scientists must work from afar, combining data from many angles. They use thermal maps, eruption timing, and even the color and composition of lava deposits to guess at what's happening below. Different types of magma might rise in different ways. Thicker magma might build more pressure before breaking out. Thinner magma might ooze through cracks more easily. These differences affect how and when eruptions occur. In some areas, the crust itself may be thinner, making it easier for magma to reach the surface. In others, older, hardened layers may resist intrusion, forcing magma to find new paths or build up for longer. These variations create a patchwork of activity across Io. Some regions light up with eruptions year after year. Others stay quiet, waiting for the next crack to open. The idea of shallow plumbing systems is not unique to Io. Earth has them too. Before a volcano like Mount St. Helens erupts, magma intrudes into underground chambers. On Mars, giant dikes once cut across the crust, feeding ancient lava plains. But on Io, this system is still active and far more extreme. The thin crust, constant tidal flexing, and fast resurfacing make for a dynamic environment where magma is always on the move. Some scientists even believe that understanding Io's shallow plumbing might help explain volcanic processes elsewhere. On Earth, many volcanoes are hard to study directly. They're dangerous, remote, or covered in vegetation. But Io lays its activity bare, stripped of water, atmosphere, or forests. Its eruptions are raw and frequent. In this way, the Moon becomes a kind of natural laboratory, a place to study volcanic plumbing at a scale and frequency unmatched anywhere else. The everlasting friction, Io's orbit as a geological power source. The idea that a moon can stay geologically active for billions of years without any internal fuel source sounds impossible at first. But Io does exactly that. The total energy budget of Io is enormous. It outputs more internal heat than any other rocky body in the solar system besides Earth, despite being much smaller. Most of that heat is being generated inside Io by the outside force of Jupiter's gravity. That distinction matters. Io isn't using up stored heat, it's creating heat as long as the orbital system stays in place, and that system is remarkably stable. For as long as Europa and Ganymede stay in resonance with Io, and there's no reason to think they won't, the whole process will continue. This makes Io one of the best examples of a gravitational energy conversion system in the solar system. Most moons and planets generate heat from leftover formation energy or radioactive decay. Over billions of years, those heat sources fade. Moons cool off, surfaces freeze. But not Io. Its energy isn't running out. It's being refreshed constantly. That's why its volcanoes are still so active. And that's why Io doesn't resemble any other moon. Scientists have studied this system using models of orbital dynamics and internal heat flow. By simulating how Io responds to tidal forces over long periods, they've shown that this heating process can remain stable for billions of years. As Io flexes, the energy spreads through its silicate mantle, reaches the crust, and finally escapes through volcanoes and surface flows. But the internal heat doesn't escape fast enough to cool the system. Instead, the orbital forcing keeps injecting more energy, maintaining a steady state. There are hints that this kind of system may exist elsewhere. Some distant exoplanets might experience similar tidal heating if they orbit close to massive worlds in tightly packed systems. But in our solar system, Io remains the clearest case. The crust of Io bears the marks of this everlasting friction. It's constantly being broken and resurfaced. Everything is in motion because the energy beneath the surface never stops. The thinness of the crust in some areas, the swelling of magma chambers, the frequent eruptions, all of it is tied to the relentless input of gravitational stress. Even the lack of long-term cooling is unusual. Most moons would eventually form a thick outer shell that traps heat and prevents rapid surface changes. But Io doesn't have time for that. The heat is too strong and too constant. The crust doesn't get the chance to settle and thicken. It remains active, porous, and unstable in places, always reshaped from below. Io's orbit doesn't just define where it travels, it defines what it is. Few other places in the solar system offer such a tight connection between motion and geology. Understanding Io's long-term energy budget tells us more about how moons can stay active without the usual sources of energy, and it hints at what may happen in other parts of the universe, where gravitational interactions are just as complex. Mapping Io's internal energy flow. To understand Io, scientists have to figure out how heat moves inside the Moon. On Earth, heat mostly travels up from the mantle in slow-moving convection cells, builds pressure, and erupts through cracks in the crust. To answer this question, scientists have turned to thermal imaging and geophysical mapping. These tools allow researchers to actually see where Io is hottest, both on the surface and just beneath it. Starting with data from Galileo in the 1990s, and later improved by Earth-based infrared telescopes and observations from missions like Juno, a pattern has emerged. The surface of Io glows with hundreds of small heat sources, scattered across its face like dots of fire. Many of these are volcanoes, but others are warm spots without obvious eruptions. Some of them are areas of steady heat loss, while others flare up and then cool again. The most important tool in this investigation has been infrared sensing. Volcanoes like Loki, Pele and Tvashtar shine brightly in thermal maps, sometimes outshining the rest of the moon combined. But the thermal glow isn't always centered on the biggest eruptions. Instead, the heat appears in long, curving lines that sometimes stretch hundreds of kilometers. These patterns suggest that heat can travel laterally through the crust and near-surface layers before it finally escapes. Instruments like the Near-Infrared Mapping Spectrometer, or NIMS, on board Galileo have provided detailed views of how temperatures change over time. At some volcanoes, the heat levels remain steady for months or years, suggesting a deep, stable connection to an interior heat source. Other areas, like flow fields, show pulsing patterns. These cycles hint at magma moving through underground pipes or chambers, pooling and then breaking through the surface again. What's remarkable is how much heat Io gives off, even in places where nothing appears to be erupting at the moment. Researchers have tried to map all of this into a kind of thermal blueprint. From these maps, it seems that Io's heat flow is focused around certain latitudes and longitudes. Many of the most active volcanic regions sit near the equator. Polar regions are cooler, though not entirely quiet. This uneven distribution helps scientists build models of what's going on inside. For example, the fact that heat is clustered near the equator might suggest that the tidal flexing from Jupiter is strongest there. Or it might mean that the crust is thinner in those regions, letting more heat escape. Some models suggest a partially molten layer sits beneath Io's outer crust that acts like a magma sponge, collecting heat from deeper down and then channeling it into networks of dikes and sills. These features, if present, would help explain the long warm bands seen in infrared images. Heat doesn't always move straight upward. It can spread sideways first, then punch through wherever the crust is weakest. Another clue comes from the way different volcanoes behave over time. Some operate on a kind of predictable rhythm. Loki's surface periodically overturns, like a giant lava conveyor belt. The timing of its eruptions matches up well with changes in Io's orbital position. That supports the idea that heat is moving through layers that respond quickly to pressure changes, not just slow, deep magma chambers, but faster, shallower systems. Observations in the mid-infrared range have also revealed hidden heat sources. These are warm areas that don't show up in visible light and may not even have a surface vent. They could be signs of slow, steady lava flows beneath a crust of cooled rock, or underground intrusions that never quite break through. These hidden sources tell researchers that Io's heat budget is more complex than just counting eruptions. Much of the energy is being lost in quiet ways: slow oozing, gentle warming, and long-lived hotspots. In addition to space-based data, scientists have used ground-based telescopes to watch Io's thermal behavior during eclipses. When Jupiter casts its shadow over Io, the surface cools quickly, but volcanoes and hotspots stay warm, glowing faintly even without sunlight. By watching how fast or slow the heat fades, scientists can measure how deep the heat comes from. Rapid cooling usually means a thin lava crust. Slow cooling means deeper or more insulated heat sources. These observations give rough estimates of lava thickness, eruption history, and the thermal properties of the crust. Putting all this together, researchers have created global heat flow maps of Io. These maps show that the total energy flowing out of Io is more than 10 times what Earth's moon gives off. Most of it is tied directly to tidal heating, but the patterns of heat loss are not even. Some areas seem to leak more energy than others, even if they don't have more eruptions. This points to differences in crust thickness, magma pathways, and possibly even the presence of underground lakes or pockets of partially melted rock. Some theories propose that Io has a thin lithosphere riding over a soft, ductile layer of hot rock. This structure would let heat pool and travel beneath the crust before finding an exit. The surface then acts like a patchwork, with weak zones becoming temporary vents. Over time, as lava flows cool and harden, new weak zones open up somewhere else. This constant shifting of heat and crust may be why Io's surface looks like it's always in motion, even when it's not erupting everywhere at once. A lander with a heat probe could measure temperature directly below the surface. An orbiter with better infrared sensors could track changes in real time. Even just higher resolution imaging could reveal cracks, vents, and bulges that mark where heat is being lost. But until then, thermal maps remain the best way to read Io's hidden structure. They show a moon glowing from within, channeling energy through a crust that never stays still for long. Pillars of fire, Io's explosive plumes that rise hundreds of kilometers. On Earth, volcanic columns can reach impressive heights, tens of kilometers in the most powerful cases. But Io takes volcanic activity to a completely different level. On this moon, towering plumes of gas and dust can shoot up hundreds of kilometers into space, far beyond anything ever seen on Earth. These are explosions so massive, they lift material above the moon's entire surface curvature and into orbit-like arcs, painting dark rings across the land where they fall. The most dramatic example of this kind of eruption came during the Voyager missions in 1979, when NASA spacecraft first observed what looked like a fountain of material blasting from Io's surface. The plume was caught mid-eruption, reaching nearly 300 kilometers into space. It was one of the biggest surprises in planetary science at the time. No one had expected to find such explosive activity on a moon so far from the Sun. Since then, dozens of similar plumes have been observed, and they continue to fascinate researchers for what they reveal about Io's nature. Earth's volcanic eruptions are shaped and limited by the thick atmosphere. As magma rises, it releases gases like water vapor, carbon dioxide, and sulfur dioxide. These gases expand and push the material upward, but they also meet resistance from air pressure, which slows them down. On Io, the atmosphere is so thin, less than a billionth the pressure of Earth's, that there is virtually no resistance. When pressurized gas explodes from a vent, there's nothing to hold it back. It surges into space with incredible force, carrying dust, ash, and small bits of frozen sulfur high above the surface. These plumes fall into two general categories. The first are called Prometheus-type plumes. They're relatively low, often under 100 kilometers tall, and come from lava flows running over patches of frozen sulfur dioxide. The heat from the lava causes the frozen gas to flash into vapor, which escapes explosively and carries material upward. This is more like a secondary explosion, an interaction between lava and a surface deposit. These eruptions are often long-lasting, as lava continues to move across the ground. The second type, much more dramatic, are Pelly-type plumes. These are direct volcanic explosions, where gas-rich magma rises quickly through the crust and bursts through vents under extreme pressure. When the vent cracks open, the sudden release of gas launches dust and droplets of molten sulfur into the sky. These plumes are often short-lived, but reach extreme heights. They can form umbrella-like clouds that fan outward before falling back to the surface in wide rings. The scale of these plumes is staggering. For comparison, Earth's Mount Pinatubo eruption in 1991 sent ash about 35 kilometers into the atmosphere. That was one of the largest eruptions in recent history, and it affected global climate. On Io, eruptions nearly 10 times taller are not unusual. But the lack of air pressure means these plumes don't behave the same way. There's no ceiling to slow them down. Once ejected, the particles follow ballistic paths, arcing like thrown stones until they fall back to the surface. And because of Io's low gravity, those arcs can be very long. Some particles land hundreds of kilometers from their source, forming dark circular patterns that mark the edges of old plumes. Thermal and optical imaging has allowed scientists to study the structure of these plumes in detail. High-speed cameras and filters sensitive to different wavelengths can reveal gas at various temperatures and compositions. Some plumes glow in visible light, others in ultraviolet or infrared. From this, researchers have learned that the plumes are mostly made of sulfur dioxide gas, along with tiny grains of sulfur, sodium, and other volcanic dust. The glowing arcs seen around some of the biggest plumes are actually made of sodium atoms, ionized by sunlight and glowing like neon signs in space. These towering eruptions play an active role in shaping Io's environment. As particles fall back to the surface, they coat the land in thin layers of new material. Over time, this constant dusting erases older features. Some particles don't come back down at all. Instead, they escape Io's gravity entirely and enter orbit around Jupiter. These tiny fragments feed the plasma torus that surrounds the giant planet. Others follow curved paths along magnetic field lines, creating glowing auroras in Jupiter's atmosphere when they strike it at high speeds. The height and structure of a plume tell researchers how much gas was trapped, how fast it escaped, and how deep the magma was when the pressure began to rise. This, in turn, helps model Io's shallow subsurface. The plumes are like pressure valves that let the Moon release some of its intense internal energy. Interestingly, not all plumes come from visible volcanoes. Some erupt from flat plains where no obvious vent or mountain exists. These stealth eruptions may come from underground sources that haven't fully broken the surface or may be linked to lava flowing below a crust of solid rock. Because of the scale of these events, they're surprisingly easy to observe even from Earth. Powerful ground-based telescopes can spot plume shadows during Io's transits across Jupiter's disk. These shadows appear as faint dark marks next to the Moon, tracing the path of the plume. In some cases, observers can even estimate the height and composition of a plume from its brightness and color. On Earth, much of the heat escapes through slow processes like plate tectonics or seafloor spreading. Io, by contrast, vents its energy in violent bursts. Each plume is an announcement from inside the Moon that pressure has built, gas has been trapped, and a sudden release has shaken the surface. Future missions may one day fly directly through a plume, sampling its gas and dust to learn more about Io's chemistry. But for now, scientists continue to watch from afar, tracking each new explosion as it rises into the cold vacuum. Patera, flows, and caldera collapses. Io's unique volcanic lexicon. Scientists have spent years trying to make sense of Io's complex geography, and in doing so, they've built a unique vocabulary just for this moon. While terms like volcano and crater are used throughout the solar system, on Io, you'll often hear words like patera, flow field, and caldera, collapse. At first glance, a patera looks like a crater. It's a large, roughly circular depression in the ground, often dozens or even hundreds of kilometers wide. But when you look closely, it's clear these aren't created by impacts. Their rims are jagged and uneven. Their floors are often lower than the surrounding land. Many are filled with lava, some still glowing hot. Unlike classic craters made by meteors, paterae on Io are volcanic in nature. They're shaped by erosion, collapse, and lava flow, not by things falling from space. One of the most famous paterae is Loki Patera. It's not only the largest volcanic feature on Io, but one of the most powerful volcanoes in the solar system. Loki is over 200 kilometers across and shaped more like a horseshoe than a circle. Io is covered with more than 400 paterae, each one its own type of volcano. Some have steep sides and look like bowls. Others are wide and shallow, spread out over flat terrain. What they all have in common is that they're places where lava has either erupted or pooled. Some paterae form when magma under the surface causes the crust to swell, then collapses when the pressure drops. Others form when lava eats away at the ground from below, hollowing it out until the top falls in. They are the scars left behind by the moon's violent internal changes. Then there are the flows, the rivers of lava that stretch out from these paterae like long fingers. On Earth, lava flows can extend for kilometers. On Io, they go much farther. Some of the longest flows ever recorded in the solar system are found here, measuring up to 500 kilometers in length. That's like a lava river stretching from New York to Washington, D.C., and they're not slow, creeping movements either. Some flows on Io happen fast, spreading across the land in days or even hours. They move through channels, pour over cliffs, and fill low basins, changing the surface at a pace that would be impossible on Earth. The reason these flows can travel so far lies in their composition and temperature. Io's lava isn't like the basaltic rock seen in places like Hawaii. In many cases, it appears to be made of ultramafic material, very rich in magnesium and iron, which can reach temperatures over 1600 degrees Celsius. That's several hundred degrees hotter than typical terrestrial lava. Because it's so hot and runny, it stays liquid longer and flows faster. Some areas show what looks like lava flooding across older terrain, covering old Patera floors, filling fractures, and spreading out into broad plains. Many flow fields have glowing hotspots at their edges, where new lava is breaking through. Some of the older flows are coated in sulfur frost. Others have turned black, indicating recent heat or fresh exposure. From orbit, these patterns are easy to see. Another feature common on Io is the caldera collapse. While this term is familiar from Earth, used to describe the sudden sinking of land following an eruption, Io's collapses can be far more extreme. A caldera on Earth might be a few kilometers across. On Io, some can be over 100 kilometers wide. They form when a magma chamber under the surface empties rapidly, often during a massive eruption. Without that internal pressure, the ground above caves in. What's left is a huge sunken area, often surrounded by steep cliffs. Unlike Earth, where erosion from rain and wind softens the edges of calderas over time, Io's version stays sharp. There's no weather here, so once a feature forms, it stays visible until it's covered by something else. As a result, caldera walls can remain as steep as when they first collapsed, with sheer drops of hundreds of meters. Some calderas contain new lava lakes, while others are empty, dusty basins waiting for the next eruption. Sometimes paterae, flows, and calderas all interact. A lava flow might begin inside a patera, erupt from a vent along its edge, then extend out across the plains. After the eruption ends, the empty chamber beneath might cause the floor to collapse, turning the patera into a caldera. Then, gases escaping from the newly exposed lava might create a plume, connecting all these processes in a single explosive event. On Io, one kind of activity flows into another, and the terrain is constantly reshaped. The sheer number of these features is staggering. Earth, with all its continents and volcanoes, has far fewer active volcanic sites than Io. Most of our knowledge comes from flybys, telescopes, and distant imaging. Yet even with those limited tools, the details are clear. Every square kilometer of Io seems to have been burned, broken, or buried at least once. Loki Patera's rhythm, the volcanic heartbeat of Io. When spacecraft first took images of Loki Patera, it didn't look like a single mountain or crater. It looked like a landform carved by shifting forces. Too irregular to be a caldera, too deep to be just a lava lake, and too smooth to be a typical crater. It didn't fit any single label. Over time, it became clear. Loki is a type of volcano unlike any seen before. Rather than erupting in sudden bursts, Loki changes in brightness in a steady, measured way. Infrared telescopes have watched it closely for decades, tracking how it glows, dims, then glows again in a repeating cycle. The timing isn't perfect every time, but on average, Loki brightens every 450 days. The heat signature tells us that fresh, hot lava is being exposed to space, making Loki's surface warmer, and therefore brighter in the infrared. On Earth, volcanoes erupt when pressure builds up. But this didn't look like a single eruption every 450 days. There was no plume, no expanding flow fields, and no change in shape. Loki wasn't blasting material into space. Instead, the glow seemed to spread slowly across the surface of the Patera, like a wave moving through molten rock. That wave, it turns out, was the surface itself overturning. What scientists now believe is happening is that the top layer of lava inside Loki Patera hardens into a crust. It floats on the surface for a time, weeks, even months, cooling and darkening. But underneath, the lava is still hot, still churning. Over time, the crust becomes unstable. It thickens and cracks. Then, without warning, it begins to sink. Not all at once, but in a sweeping front, like a giant ice sheet breaking off into the sea. As the old surface drops into the lava lake, fresh molten rock rises to replace it. That new lava is much hotter, and it glows brighter in the infrared. This resurfacing front moves from one side of the Patera to the other, often starting near the western edge and sweeping east over the course of several weeks. It's like watching a ripple slowly move across the surface of a pond. But instead of water, it's lava that's hundreds of degrees hotter than anything found on Earth. The cycle then resets. A new crust begins to form. The bright signature fades. Then it builds again until the next collapse begins. Galileo in the 1990s confirmed what many had guessed. The brightening wasn't caused by eruptions at the edges or vents, but by internal resurfacing of the lava lake. Later observations using large infrared telescopes on Earth, including the Keck Observatory, filled in the rest of the picture. Each cycle is slightly different. Some are shorter, some are longer. But the pattern holds, with resurfacing fronts crossing Loki's floor roughly every 450 days. It's a process more like the rising and falling of magma inside Earth's calderas than anything seen on other moons. But even then, Earth lacks a good comparison. Loki doesn't act like Kilauea with its steady flows, or like Etna with explosive ash clouds. It's closer in behavior to a massive industrial furnace, sealed, pressurized, and emptied on a schedule. The lava crust is a floating layer that breaks under its own weight and movement. Models built to simulate Loki's cycle suggest that the crust thickens over time until it can no longer float. The longer it stays intact, the more likely it is to suddenly fail, triggering the resurfacing wave. The timing of the crust's collapse depends on how much heat is retained, how the magma chamber is replenished, and how the surface cools from above. Some models suggest that a slow upward leak of gases might even help support the crust, like bubbles holding up a raft, until that support weakens and the raft sinks. Each resurfacing cycle releases an incredible amount of energy. Calculations suggest that Loki Patera alone may account for nearly 10 to 15% of all the heat released by Io's surface. That's just one volcano out of hundreds. But because it's so large and so predictable, Loki gives scientists a rare chance to measure how internal heating translates into surface change. Loki's activity also affects the surroundings. When the lava is fresh and hot, sulfur gases can escape more easily, feeding Io's thin atmosphere. When the surface crust reforms, the outgassing slows. This creates a subtle connection between surface geology and atmospheric cycling. Every time a telescope watches Loki, the data is added to a growing timeline that now spans more than 3 decades. Few other volcanic systems in the solar system have been observed this steadily over such a long stretch of time. Any mission that visits Io or studies it from a distance will almost certainly target Loki. Its brightness makes it easy to find, and its rhythmic activity means there's a good chance something interesting will be happening when instruments arrive. In many ways, Loki is the most active, most revealing, and most watchable window into Io's interior. And yet, for all its familiarity, it still holds many mysteries. Scientists are still debating how deep the magma reservoir is, how thick the crust becomes before it sinks, and why some cycles are shorter than others. Some suspect that changes in Io's orbit or small shifts in tidal stress might slightly tweak the timing. Others wonder if Loki might eventually shift behavior altogether, breaking its rhythm or growing even more active. But for now, the rhythm holds, and the heart of Io beats on, slow but steady, in the cold silence around Jupiter. Lava lakes. That never cool, evidence of active replenishment. Pele sits in Io's southern hemisphere and has been a standout thermal feature since spacecraft first looked closely. A lava lake is a surface pool of molten rock, exposed to the sky and often with a thin crust that forms and breaks repeatedly. On Earth, we see lava lakes in a few special locations like Kilauea in Hawaii or Nyiragongo in Africa. But even those lakes sometimes drain or harden. On Io, the opposite seems to happen. Pélé's lake remains active over time. It doesn't freeze solid. Instead, it shows signs of movement, surface overturning, fresh lava surfacing, and consistent heat output. When Galileo passed over Io, it saw Pélé glowing with intense heat. The thermal signature was steady, broad, and consistent. The shape and intensity of the thermal data fit the pattern of a lava lake, a wide shallow feature, tens of kilometers across, that held molten rock at or near the surface. The brightness levels varied slightly over time, but the core remained hot and active. The steady nature of this glow suggested something else too: replenishment. A lava lake on its own should cool fairly quickly. Without fresh magma rising from below, the surface would form a thick crust and the heat would fade. That's not what happens at Pélé. Instead, it stays hot. The crust seems to break apart again and again, letting new lava rise and spread. This pattern points to a deep connection with Io's magma system. Somewhere below, a reservoir must be sending up molten rock in a slow, constant supply. The old lava rises, floats to the top, releases heat, and is either cycled downward or spilled onto the surface. Unlike Loki Patera, Pélé doesn't have a clear cycle. Instead, it behaves like a constant engine, always warm, always active. The size of Pélé's lava lake is also worth noting. It may stretch 30 to 50 kilometers across. That's larger than most lava lakes on Earth. The scale of this feature means that large amounts of magma must be involved. It's a massive structure, with magma likely coming from a deep chamber connected to Io's molten interior. The energy needed to keep this system running comes from the same tidal forces that drive all of Io's volcanism. But at Pélé, those forces seem to keep the plumbing open and flowing without pause. The lake itself is likely made of silicate lava, similar to basalt on Earth but much hotter. Some scientists believe that it may also include sulfur or other materials near the edges. The heat in the center is too high for sulfur to stay, but on the fringes, the presence of gases and lower temperatures could allow sulfur compounds to form. This mixture of materials may give the lake its complex surface. From orbit, scientists have seen rings around Pélé, dark spots that mark the outer edges of the vent and the regions where gas has fallen as frost. These markings change slowly over time, suggesting that even the area around the lake is part of the active system. On Earth, lava lakes often drain when pressure drops or when a fissure opens and allows magma to escape elsewhere. On Io, Pélé seems to stay full. This suggests that the pressure below is constant and that the magma system is well connected. There may be a chamber below Pélé that acts like a steady pump, feeding the surface even as material is lost to cooling or eruption. The flow of energy in this system is also impressive. Pélé gives off enormous amounts of heat. Estimates suggest that it may emit over 1 terawatt of thermal energy, comparable to some of the largest power plants on Earth. Monitoring these kinds of features requires long-term observation. Potential future missions, like the proposed Io Volcano Observer, would carry high-resolution cameras and spectrometers to measure the lake's composition, temperature, and surface changes in detail. These tools could finally tell us exactly how Pélé works, how deep the magma goes, how fast it rises, and how the lake reshapes itself over time. The sulfur cycle from hell, unpacking Io's geochemical anomalies. Io doesn't have water like Earth does. What it does have in great abundance is sulfur. Sulfur isn't just part of Io's makeup, it is the cycle that defines its landscape. On Earth, we live by the rock-water cycle, where water flows from clouds to rivers to oceans and back again. On Io, the entire system works through sulfur and sulfur dioxide. The cycle begins deep below the surface, inside Io's crust, where sulfur-rich magma forms. This magma contains silicates, but it's also rich in sulfur and compounds like sulfur dioxide. These lighter materials bubble and vaporize easily, creating pressure that helps drive eruptions. When a vent opens, these gases escape into the vacuum of space or fall back to the surface. The first stage of the sulfur cycle is violent release, volcanic eruptions that launch sulfur. Close to the vents, the ground can reach over 1,300 degrees Celsius. In that kind of heat, sulfur directly sublimates from solid to gas. The same thing happens with sulfur dioxide ice when sunlight hits it. It vanishes straight into gas, rising into the atmosphere or drifting into space. That creates local clouds of sulfur vapor, which shift with the sunlight and the moon's rotation. As Io moves in and out of Jupiter's shadow, the temperature difference drives a strange kind of weather, if you can call it that. The sulfur and sulfur dioxide can condense near the surface, forming frost. It can collect in colder areas, at higher elevations, or on the outer edges of lava fields. These frosts are fragile and temporary. As soon as sunlight returns or a new eruption changes the local temperature, they begin to sublimate again. The cycle repeats endlessly. The sulfur plays a big role in coloring the moon. Observations from orbit have shown a full palette of hues. Yellows from elemental sulfur, reds from short-chain sulfur molecules, whites from sulfur dioxide frost, and even blacks and greens in areas where mixtures form. The colors tell scientists what kind of compounds are present and how recent an eruption might have been. Brighter frost often means a newer deposit. Darker flows may indicate older lava that's lost its coating of sulfur frost. Some areas cycle between colors as new materials are laid down, baked, and then overlaid again. In areas where eruptions have paused, sulfur deposits can build up in layers. Some may be soft and powdery, others hardened into crusts. These layers can fracture, collapse, or get buried by the next wave of molten rock. Sometimes they form plateaus or ridges. Other times they break apart into oddly shaped pits and valleys. Without wind or rain to erode them, the surface features are shaped mostly by heating, cracking, and falling debris. It's a chaotic, ever-changing system. There are no stable coastlines or riverbeds. There are no glaciers or rainstorms to cut valleys. Instead, the sulfur cycle rules everything. It dictates how the surface looks, how the air behaves, and even how Io interacts with the space around it. And it's a system that can't exist on Earth. Our sulfur stays locked in rocks or dissolves in ocean water. On Io it flows like water, rains like snow, and forms clouds that disappear when the sun hits them. How thick are the sulfur layers in different areas? How fast do they build up or vanish? What roles do temperature, magnetism, and surface texture play in moving sulfur from place to place? These are questions that can't be fully answered from orbit alone. They call for close-up study, maybe even landers or sampling missions someday. Until then, we watch from afar as Io continues its strange chemical ballet. The eclipse clock, how Io became a tool of 17th century navigation. Longitude was a puzzle that had haunted sailors and navigators for generations. Latitude was easy enough. By measuring the height of the sun at noon or the position of the North Star at night, one could figure out how far north or south they were. But knowing how far east or west they had traveled required something much harder: keeping accurate time. The Earth spins at a steady rate, 360 degrees in 24 hours. That means for every hour of difference between your local time and a reference time, like Greenwich, you've moved 15 degrees of longitude. If you know when it's noon where you are, and you also know what time it is back at a reference point, you can work out how far around the planet you've moved. The problem was, clocks in the 1600s weren't reliable enough. Pendulums swung differently on moving ships, temperature changes threw off the mechanisms, and sailors couldn't trust their watches to stay accurate for long voyages. Without dependable clocks, they couldn't calculate longitude at sea with any real precision. That's where Io came in. Romer was not thinking about navigation when he started watching Io in the 1670s, but those eclipse timings had another use. They provided a kind of celestial schedule, a table of predicted events that should happen at specific times, down to the second. If a sailor at sea could watch Io and record when an eclipse occurred, he could compare that to a table prepared in advance. If the eclipse happened later than predicted, he was west of the reference point. If it happened earlier, he was east. In this way, Io became a kind of cosmic timekeeper, offering a way to check the clock without needing a mechanical one. This method was promising, and many navigators and astronomers took it seriously. The French astronomer Jean Picard and the Italian Giovanni Domenico Cassini, working at the Paris Observatory, began building eclipse tables for Io and the other Galilean moons. These tables were accurate enough to determine longitude on land to within a few dozen miles, a significant improvement over earlier guesses. From mountain observatories in Europe, from colonial outposts in the Americas, and from coastal cities around the world, observers began watching Jupiter's moons. The real challenge was at sea. Watching Io's eclipses requires a telescope and a steady view of the sky. On land, this wasn't a problem, but on a rolling ship with masts swaying and clouds drifting in and out, it was much harder. The precision required to see the moment when Io slipped into Jupiter's shadow or emerged from it was difficult to achieve from a moving deck. Timing errors of even a few seconds could throw off the result. And while the idea worked in theory, the practice of using Io as a clock turned out to be better suited for surveyors and astronomers on solid ground. Even so, the technique didn't disappear. It became a valuable way to fix the longitudes of key locations around the world. Surveying teams in far-off places, Brazil, Africa, India, would observe Io's eclipses and compare them to tables calculated in Paris or London. This helped refine maps and update nautical charts. It made the world feel a little smaller, a little more measurable. One famous example came from the French Academy of Sciences, which sent teams to South America in the 18th century to determine the shape of the Earth. Part of their job was to measure distances between key points. By using the eclipses, they could pin down the longitude of their observatories, even deep in unfamiliar territory. In this way, Io contributed to the ongoing argument about whether the Earth was flattened at the poles or bulged at the equator, a question that needed exact longitude data to answer. Eventually, the development of the marine chronometer in the 18th century made the eclipse method less necessary for sailors. These new clocks, built by craftsmen like John Harrison, were precise enough to keep accurate time over long voyages. With a good chronometer and a sextant, a skilled navigator could measure the sun's position and calculate longitude without needing to look at Jupiter at all. The marine chronometer won prizes and changed navigation forever. But for a brief window of time, Io was at the center of the effort. It's remarkable to think about how a moon so far away could be part of everyday human travel. Long before we sent spacecraft past its surface, or even knew what it looked like, Io played a quiet role in helping people find their way across the seas. The regularity of its eclipses gave humans something solid to rely on in an age when most tools were still unpredictable. And even though the method didn't become common on ships, it hinted at a future when the sky could offer more than mystery. It could offer guidance. Juno's side glances, what the current mission is seeing from afar. Juno's mission to Jupiter wasn't designed with Io in mind. The spacecraft's primary mission is to study the planet itself, its deep atmosphere, its magnetosphere, and its interior structure. However, Juno's highly elliptical orbit around Jupiter, which brings it close to the planet and then swings it out to distant regions of the solar system, allows it to take occasional side glances at Jupiter's moons, including Io. These brief high-altitude passes have provided some unexpected insights into the volcanic moon, despite Juno's main instruments not being optimized for close-up observations like those of Galileo. One of the most valuable data sources Juno collects about Io is magnetic field information. While the spacecraft's instruments aren't able to capture detailed surface images of Io, they can still detect how the moon interacts with Jupiter's powerful magnetic field as it orbits. These interactions are crucial for understanding Io's internal dynamics, particularly the role of tidal forces in driving the volcanic activity that makes the moon so geologically active. Juno's magnetometer, which is designed to study Jupiter's magnetosphere in depth, is also capable of detecting the magnetic signals produced by Io's interaction with that magnetosphere. As Io moves through Jupiter's magnetic field, it creates a kind of magnetic wake. By measuring these changes in the magnetic field, Juno can provide detailed information about the strength and structure of Io's own magnetic field, as well as the electromagnetic environment around it. In addition to the magnetometer, Juno also carries a gravity science experiment that has helped researchers learn more about Io's internal structure. Although Juno doesn't fly close enough to Io to obtain detailed gravity data, the spacecraft's flybys of Jupiter and its moons allow it to indirectly measure the gravitational influence that Io has on the spacecraft's trajectory. By observing the way Juno's orbit shifts as it passes near Io, scientists can infer information about the moon's mass distribution, its internal structure, and the way its dense interior materials are arranged. When Juno flies close to Jupiter, the spacecraft passes through the areas of the planet's magnetic field that are shaped by the interactions of Io and the other moons. As it moves through these regions, the spacecraft experiences tiny changes in its velocity due to the gravitational influence of the moon. This shift, although small, is detectable by Juno's tracking systems, which measure the spacecraft's position very precisely. These small gravitational anomalies provide insights into Io's composition and structure, particularly the way its dense silicate mantle and molten interior are arranged. These gravity measurements can also help scientists learn more about the depths of Io's volcanic activity. In particular, they provide clues about whether the moon has a partially molten layer beneath its surface, as many scientists suspect. The gravity data suggests that Io has a very uneven distribution of mass, which could be due to the presence of molten material beneath its crust. Such data helps to confirm the theories about the moon's internal composition, providing an important piece of the puzzle about how Io remains so geologically active. While Juno is not equipped to measure the moon's surface directly or to detect individual volcanic plumes, its instruments are able to capture data on the ionized gas around Io. As the moon's volcanic eruptions send gases like sulfur and oxygen into space, they become ionized by Jupiter. Juno's instruments can measure the density and distribution of these ions, offering a glimpse into the nature of Io's tenuous atmosphere and how it interacts with Jupiter's magnetosphere. By measuring the composition of this cloud, Juno's instruments can help scientists determine how much material Io is contributing to the larger system and how that material flows and interacts with the planet's radiation belts. As it orbits Jupiter, the spacecraft experiences Jupiter's powerful radiation belts, which are heavily influenced by the volcanic activity on Io. When Juno passes near the planet, the radiation from Io's volcanic plumes is detected and studied. This allows scientists to link the volcanic activity on Io with changes in Jupiter's radiation environment, providing a more complete picture of how Io's volcanism feeds into the broader dynamics of the Jovian system. The key advantage of Juno's orbit is that it allows the spacecraft to perform detailed studies of the entire Jupiter system, not just focusing on Io. The spacecraft's elliptical orbit brings it near the moons, and from these vantage points, Juno is able to collect data on Io from afar. While this is not a substitute for direct imaging, the data Juno collects complements the detailed surface studies provided by earlier missions, providing a more comprehensive understanding of Io's behavior over time. Unflown paths, the cancelled missions that could have changed everything. Io is one of the most tantalizing objects in the solar system. However, despite the successes of missions like Galileo, there have been numerous proposed missions that never made it off the ground, each with the potential to vastly expand our understanding of this volatile moon. One such mission was the Io Observer, a proposed spacecraft designed specifically to focus on Io and its volcanic activity. This mission was part of a broader initiative under NASA's line of missions called the New Frontiers program, which was aimed at exploring the outer planets and their moons. The Io Observer was initially proposed in the early 2000s as a way to follow up on the discoveries made by Galileo. Although the spacecraft never received approval to launch, the proposed mission was an ambitious attempt to study Io in greater detail than ever before. The Io observer would have been equipped with a suite of instruments designed to map the surface of Io in high resolution, measure the composition of its volcanic plumes, and analyze the interactions between the Moon's magnetic field and Jupiter's powerful magnetosphere. One of the key goals of the mission would have been to track changes in the surface of Io over time, offering a level of detail that would have far surpassed what Galileo was able to provide. Scientists hoped to use the mission to investigate whether the interior structure of Io was indeed responsible for its extreme volcanic activity, or whether other, more exotic processes were at play. Despite its promising design, the Io observer never received the funding needed to become a reality. NASA ultimately cancelled the mission in favor of other projects, notably missions focused on Mars and the study of asteroids. The cancellation was a major disappointment for planetary scientists, as the Io observer could have provided essential data that would have helped answer fundamental questions about Io's geology, its interior, and the forces driving its volcanic eruptions. Europa Clipper will focus on Europa, Jupiter's icy moon, and its potential for hosting life beneath its frozen surface. However, one of the concepts for the mission, which was discussed during the planning stages, involved flybys of Io as it traveled on its way to Europa. These flybys would have given the spacecraft an opportunity to perform detailed studies of Io's volcanic activity and its interactions with Jupiter's magnetic field. Europa Clipper's planned flybys of Io were not included in the final mission design due to budget constraints, but they would have provided an invaluable opportunity to observe Io's ongoing volcanic eruptions in real time, especially in the context of the planet's broader environment. The mission would have helped clarify the mechanisms behind the volcanoes and given us more information about the composition of the volcanic plumes, the amount of heat they release, and how Io's atmosphere interacts with the surrounding space. The Europa Clipper's cancellation of Io flybys meant that scientists were left with limited options for future dedicated missions to the Moon. Some proposals focused on sending a small lander or even a probe to the surface of Io to capture images and study its volcanic activity up close. These landers would have been capable of analyzing the lava flows, measuring surface temperatures, and taking detailed photographs of the volcanoes and Patera. While such missions are incredibly difficult due to the extreme conditions on Io, proposals for surface exploration would have provided a unique perspective on Io that orbiters simply could not achieve. One proposal, called the Io lander, would have attempted to touch down on the surface of the Moon and deploy instruments to measure the volcanic activity directly. Given Io's lack of atmosphere and the continuous volcanic eruptions, any spacecraft attempting to land would have faced significant challenges. The Io lander would have been designed with radiation shielding and advanced materials that could have allowed it to survive long enough to send back valuable data about the surface and subsurface structure of the Moon. Unfortunately, this lander mission was never approved, and the concept was eventually shelved. The same fate befell other lander proposals, each cancelled due to the extreme challenges of landing on a Moon with active volcanism, high radiation, and an unpredictable surface. The cancellation of many of these proposed missions underscores the difficulty of studying a Moon as extreme as Io. It represents a unique challenge for planetary scientists. The missions that were never launched would have further filled in the gaps of our knowledge, providing a much deeper understanding of Io's geological processes and its role in the larger Jupiter system. Each cancelled mission represents an opportunity lost, and while the data we have is remarkable, we can only imagine what might have been discovered if these missions had been allowed to proceed. As we continue to explore Jupiter and its moons, we can only hope that future missions will pick up where these cancelled ideas left off, giving us a closer look at the wonders of Io. Life in lava? Could extremophiles survive on Io's fiery surface? To understand the potential for life on Io, we first need to consider the kinds of microorganisms that live in extreme conditions on Earth. These are organisms known as extremophiles, and they are found in some of the harshest environments imaginable. From the searing heat of hydrothermal vents on the ocean floor, where temperatures can reach over 100 degrees Celsius or 212 degrees Fahrenheit, to the frozen deserts of Antarctica, where organisms can survive with minimal liquid water, extremophiles have proven time and again that life can find a way to survive in environments that most organisms would consider lethal. Many of these extremophiles belong to a group known as thermophiles, organisms that can survive and even thrive at high temperatures. On Earth, thermophiles can live in environments that are much hotter than boiling water. Some of the most heat-tolerant microbes, such as Thermus aquaticus, have been found to survive in temperatures close to 80 degrees Celsius in hot springs, while others, known as hyperthermophiles, can survive at temperatures exceeding 100 degrees Celsius. In fact, these organisms are not just surviving, they are metabolizing and reproducing. This remarkable ability to withstand extreme heat has led scientists to wonder if similar life forms could exist on Io, where the surface temperatures in some areas exceed 1,500 degrees Celsius in the immediate vicinity of lava flows and volcanic vents. However, the question of whether extremophiles could survive on Io is complicated by several factors. For one, Io's surface is constantly changing due to the intense volcanic activity. The Moon's surface is perpetually reshaped by the eruptions of its volcanoes. Additionally, the sulfur on Io is not the same as the hot springs or volcanic environments on Earth. On Io, sulfur exists in a different state, molten sulfur, which has a much lower boiling point than water and behaves differently than liquid water. This brings us to the first question. Could extremophiles survive in molten sulfur, given the lack of water? While liquid water is considered essential for life as we know it, it is not the only solvent capable of supporting life. Some earthbound extremophiles can survive in environments with very little water, relying on other substances for their chemical processes. For example, some microorganisms found near volcanic vents on Earth use sulfur as an energy source. These sulfur-loving microbes, called sulfur bacteria, utilize the chemical energy in sulfur compounds to fuel their metabolism, much like plants use sunlight in photosynthesis. On Io, the surface is rich in sulfur compounds, and it's possible that organisms could adapt to use sulfur in a similar way. Furthermore, even if sulfur is not as hospitable to life as water, some researchers have hypothesized that the byproducts of Io's volcanoes might create areas where liquid sulfur and water could coexist temporarily. For example, when sulfur is heated and vaporized by volcanic activity, it can mix with other elements in the atmosphere, such as oxygen and hydrogen. If conditions were right, this mixture could potentially form sulfuric acid, a substance that is capable of dissolving in water. Such an environment might not be suitable for the long-term survival of Earth-like life, but it could provide a short-lived habitat for certain microorganisms, especially if they were capable of metabolizing sulfur and other compounds. The next question is whether these extremophiles would need to exist in liquid sulfur, or if they could potentially survive in the cooler regions around Io's volcanoes, where the sulfur deposits solidify. The surface of Io is covered with vast plains of solidified sulfur and its compounds, which are constantly being reshaped by volcanic activity. While these solid surfaces are much cooler than the molten sulfur near the volcanoes, they are still subject to significant radiation from Jupiter's Magnetosphere, which bathes Io in a deadly shower of energetic particles. These radiation levels would make it almost impossible for life to survive on the surface for extended periods without some form of protection. One possibility is that microorganisms could survive in the surface deposits left behind by volcanic eruptions. These deposits could form a temporary shield against the harsh radiation. Similar to how extremophiles on Earth are able to take refuge in cracks and crevices in the Earth's crust, microorganisms on Io could potentially take refuge in the layers of sulfur deposits, where they might be shielded from the worst of the radiation. While this would not protect them indefinitely, It could allow for periods of survival during less volatile phases of the Moon's volcanic activity. For organisms to truly thrive on Io's surface, they would need a steady supply of energy. On Earth, life in extreme environments often relies on chemical energy, such as that found in sulfur or methane, to fuel its metabolic processes. Could similar processes be occurring on Io? The answer could lie in the volcanic plumes that shoot high into the atmosphere. These plumes constantly replenish the surface with fresh material, creating a dynamic and ever-changing environment. If any form of life were to exist in or around these plumes, it would be constantly exposed to new sources of sulfur, which could provide the chemical energy necessary for survival. Some researchers have suggested that microorganisms could exist in the higher altitude regions of the Moon's thin atmosphere, where the temperature is much cooler and more similar to Earth's conditions. While the atmosphere of Io is incredibly thin and lacks oxygen, it is rich in sulfur dioxide, which could be used by certain sulfur-eating microbes. These microorganisms would not be able to survive in the same way that life on Earth does, but they could still harness the available sulfur compounds in the atmosphere to fuel their metabolic processes. The ultimate challenge for any form of life on Io is the sheer extremity of the environment. While Earth's extremophiles have adapted to survive in extreme heat, pressure, and chemical conditions, the combination of volcanic activity, radiation, and a lack of liquid water on Io makes it one of the most inhospitable places in the solar system. Yet, the possibility that some form of life could exist, whether in molten sulfur, volcanic deposits, or higher in the atmosphere, remains an intriguing question. While we cannot rule out the possibility entirely, the extreme conditions on Io would require a form of life unlike anything we know on Earth, one capable of surviving in an environment that challenges our understanding of biology. Whether life on Io is possible or not, the investigation into these environments helps broaden our definition of habitability. It forces us to rethink what it takes for life to survive and challenges the boundaries of our knowledge about the conditions under which life might arise and thrive. Subsurface voids and hidden chambers. Could Io hide habitats below? On Earth, volcanic systems often contain magma chambers surrounded by more porous layers of cooled lava and ash. Gases and liquids can move through those layers. Sometimes underground voids form naturally when lava drains out of a tube, leaving behind hollow spaces. Other times, as magma cools unevenly, cracks and pockets open up. These are exactly the sorts of spaces where heat, moisture, and chemistry can settle together. If similar features exist on Io, and there's reason to think they might, then the Moon may have more internal variety than it shows from space. Now, what would it take for one of these voids to be considered a habitat? First, it would need to be protected, deep enough to avoid sterilizing radiation from Jupiter's magnetosphere. That protection could come from just a few kilometers of crust. Second, the area would need a temperature range that allows for some chemical activity. Not room temperature, but something that keeps things from freezing solid or evaporating instantly. And third, it would need materials. Something life could use, like sulfur compounds, trace amounts of water, maybe even ammonia or salts. It's the idea of briny reservoirs that's particularly interesting. Salt water lowers the freezing point of water, meaning that in salty mixtures, liquid can exist at much colder temperatures than pure water could. On Earth, some of the coldest lakes known, deep beneath the Antarctic ice, stay liquid year-round because they're full of salts. Could something similar exist under Io's crust? While the surface shows no sign of liquid water today, that doesn't rule out the past. Water could have been present in Io's early history, and some of it might still linger underground, chemically locked in minerals or trapped in salty pockets warmed by tidal heat. We also know that water-bearing minerals can survive on moons like Europa and Ganymede. And though Io's surface doesn't show much water, there's a chance that it exists deeper down, possibly left over from when the Moon first formed. It's also possible that even if liquid water doesn't exist, other substances, like liquid sulfur or sulfuric acid, could fill the role of a solvent, letting complex chemistry unfold. We don't have instruments directly measuring Io's interior the way we do on Mars or the Moon, but models based on gravity data, as well as indirect clues from the behavior of volcanoes and plume activity, suggest that Io's interior isn't uniform. That unevenness hints at a layered and shifting interior structure. In Earth's volcanic systems, microbes are sometimes found inside rock itself, deep underground, surviving in small fractures where gases seep through. They feed on hydrogen, sulfur, iron, or even rock minerals. In some cases, they don't need sunlight at all. Their energy comes entirely from chemical reactions. If similar reactions could happen in Io's subsurface, then those regions might host energy-rich environments. They wouldn't be easy places to live, but they'd be consistent. They might offer the one thing Io's surface can't: stability. Io is billions of years old. Its volcanic activity may be intense, but that also means it's been generating internal heat for a very long time. Over all those centuries, slow changes in its interior could have created persistent features. Voids that once held lava might now be hollow and stable. Gases released from below could have carved out chambers. Salty materials could have accumulated over long timescales, and natural insulation from overlying rock might keep them from escaping too quickly. On Earth, when we look at lava tubes or caves formed by old volcanic activity, we often find ecosystems that don't resemble surface life at all. Fungi, bacteria, and even some animals can survive entirely underground, feeding on chemical sources rather than light. While there's no reason to think Io hosts such things, the microbial world doesn't need much room to thrive. Even a tiny fissure with the right conditions could harbor colonies, shielded from the chaos outside. The big unknown, of course, is whether any of this has actually happened. Without a dedicated mission to explore Io's interior, we can only speculate based on what we know from Earth, and from moons like Europa and Enceladus, where signs of internal water are stronger. Io's subsurface could be one of the last places in the solar system where life might lurk completely undetected, quietly surviving under the crust while the surface erupts above. How do you land on Hell? Engineering challenges for Io missions. Trying to land a spacecraft on Io is like aiming for a bullseye that's moving, unstable, and on fire. It's one of the most hostile solid surfaces anywhere in the solar system. At first glance, it doesn't look that bad from orbit. A solid moon with no thick atmosphere, no storms, and clear visibility. But the real challenges don't come from what's missing. They come from what's there. The most immediate problem is the radiation. Io sits right in the middle of the most intense radiation belt in the solar system. Jupiter's magnetic field traps charged particles that zip around like bullets. Any spacecraft near Io is constantly bombarded with this radiation. It damages electronics, weakens sensors, and breaks down materials over time. Radiation shielding is possible, but it's not easy. You can wrap a spacecraft in protective layers, aluminum, lead, or composite shielding. But every kilogram of shielding adds weight. Weight means more fuel needed to get there, and shielding doesn't last forever. Even hardened electronics can fail after prolonged exposure. So the longer you stay near Io, the more likely something will break. A successful lander wouldn't just need to be shielded, it would need to work fast, complete its mission quickly, and possibly die within days or weeks. That's the kind of time frame engineers would be planning for. Then there's the heat. Not from the sun, Io is far from it, but from the surface itself. The heat near an active vent could melt metal. Even away from the volcanoes, the surface isn't safe. Volcanic plains can be covered with fresh flows, sulfuric deposits, or superheated patches. These areas can change temperature rapidly. One part might be icy in the morning and boiling hot by midday. This creates enormous challenges for landing systems. A spacecraft would need to land on something solid. But on Io, nothing stays solid for long. The ground can crack, shift, or collapse underfoot. Some regions are basically ash fields, soft, unstable, and full of gas pockets. Others are hard rock, but they sit on top of molten layers. The lander might touch down on what looks like solid ground, only to sink, tilt, or break through. To avoid this, a mission would need detailed maps of the landing site, something we don't fully have yet. Even choosing a safe spot is tricky. Io's surface is constantly reshaped by eruptions. A location that looks calm one year might explode the next. Eruptions can throw debris hundreds of kilometers high. That means even a lander far from a volcano might be pelted with falling rock, ash, or sulfur. The surface might also shift due to tidal forces changing topography. Given all that, landing gear design becomes its own challenge. A traditional four-legged lander, like those used on the Moon or Mars, might not work well here. Legs could sink into ash or snap on hard rock. Some designs consider wide, flat pads that spread out weight. Others explore soft landing techniques using airbags or deployable surfaces. Another idea is to make the lander semi-disposable, able to tilt, shift, or even be partially buried and still complete its job. Power is another big problem. Io gets only a fraction of the sunlight Earth does. Solar panels would need to be large and efficient to generate enough power. But large panels are also vulnerable to debris, dust, and radiation damage. They'd also need to fold and unfold reliably in an unstable environment. Some engineers look to radioisotope power, using a small nuclear heat source to generate electricity. That works well on Mars and deep space probes. Once on the ground, the lander would also need to survive temperature extremes. Io's night side drops far below freezing. Its day side can reach hundreds of degrees Celsius in some areas. Thermal control systems, heaters, radiators, insulation, would need to be highly adaptable. But the more systems you add, the more power you need, and the more moving parts, the more points of failure. Communication would be tricky. Io spins quickly, which means ground stations wouldn't always have a clear line of sight. Jupiter's own massive radio output can also interfere with signals. A lander might need to store data and transmit it in bursts when the line is clear. Alternatively, a relay orbiter could hover nearby to collect data and pass it along. But any relay satellite would face the same radiation problems as the lander. Autonomy would be key. Commands from Earth take almost an hour to reach Jupiter. That's too slow for real-time control. The lander would need to make quick decisions on its own: how to steer during descent, how to react to surface conditions, when to deploy instruments, and how to protect itself from hazards. That requires a level of onboard intelligence we're only now starting to develop. There's no atmosphere to slow a spacecraft with parachutes, like on Mars. That means all deceleration has to come from engines, carefully timed, carefully controlled. The engines must fire close to the surface without kicking up too much dust or debris. On Io, dust isn't just a nuisance. It can be electrically charged, sticky, and corrosive. Sulfur compounds could coat sensors, lenses, or vents, interfering with systems almost immediately. Because of all these challenges, a lander probably wouldn't last long. Unlike rovers on Mars, which can work for years, an Io lander might be considered a short-term visitor. It might be built for a single day or a few orbits. Its mission would be to collect what it can: images, heat readings, gas samples, magnetic data, and send it back fast. It would be designed to fail gracefully. If it lasted longer, that would be a bonus. Despite all these hurdles, the idea of landing on Io still holds strong appeal. The science payoff would be massive. No one's ever sampled a lava world up close. No one's seen an eruption on another planet from the ground. No one's tested the surface chemistry of active volcanoes in a place shaped by tidal forces instead of plate tectonics. If we could pull it off, even once, we'd open a window into a whole new category of planetary behavior. Ideas for landing are still being studied. Some proposals include scout missions, small impactors that crash into the surface to test hardness and chemistry. Others suggest hovercraft-style landers that never fully touch down. There's also discussion of tethered systems, where a probe lowers itself on a cable from a high-flying spacecraft and samples the surface briefly before rising again. Whatever the method, the basic facts don't change. Landing on Io means surviving intense radiation, unpredictable terrain, violent heat, and the constant threat of eruption. It's not like landing on Mars or even on Europa. It's more like trying to park a probe on the edge of an erupting volcano, while lightning strikes from every direction and the ground shakes beneath you. But for many scientists and engineers, that's exactly what makes it worth doing. Robots in the furnace: how future probes must survive Io's heat. The materials used in future Io probes can't be the same ones used on Mars rovers or lunar landers. Aluminum, common in spacecraft, begins to weaken well before 1000 Kelvin. Plastics, glues, and insulation materials melt even faster. Even titanium, often chosen for its strength and heat resistance, struggles in those conditions. So engineers must reach for a different toolbox. One answer lies in ceramics. These materials handle heat better than metals. Things like zirconia, silicon carbide, and alumina can survive in high-temperature environments and don't conduct electricity easily. That makes them useful both structurally and as insulation. Tiles made from these ceramics could form the outer shell of a probe. They wouldn't just reflect or block heat, they would tolerate it. Some of these materials are already used on the nose cones of atmospheric re-entry vehicles, where temperatures soar during descent. Another option is heat-resistant alloys. Nickel-based superalloys like Inconel are used in jet engines and power plants here on Earth. They hold up well under extreme heat and stress. For Io, their job would be to act as internal supports or shields, surrounding the probe's electronics like a metal skeleton, giving it both strength and resistance to thermal distortion. Even with tough materials, shielding alone isn't enough. You have to stop the heat from getting in at all, or at least slow it down long enough to do the job. That's where thermal insulation systems come in. On Earth, spacecraft use things like multi-layer insulation blankets, thin sheets of reflective material that bounce heat away. On Io, those won't work unless they're completely sealed and protected from the abrasive sulfur dust that coats everything. Engineers might develop new forms of insulation using aerogels, solid foams made from silica that trap air and slow down heat flow. Some aerogels are over 95% empty space and still survive high heat. Their spongy structure makes them excellent at keeping heat out, even in tight spaces. But passive systems, things that just block heat, can only do so much. In truly hot zones, especially near lava lakes or erupting vents, probes will need active cooling. That means pumping heat away from sensitive parts and dumping it somewhere else. On Earth, this is done with fluid loops, circulating liquids that absorb heat and carry it to radiators. On Io, it's harder. You can't just let heat out into the air. There is no real atmosphere. Radiators would need to dump heat directly into space, which is slow and inefficient. To work around this, engineers might use phase change systems. These involve special fluids that absorb heat by changing from a solid to a liquid, or from a liquid to a gas. As they absorb energy, they keep temperatures stable for a while. It's like how ice keeps a drink cool while it melts. Inside a lander, sealed tanks filled with waxes or metals could store that heat for the duration of a short mission. Once full, the system would shut down, and the mission would end. Another idea is to isolate the sensitive systems entirely. Instruments could be placed in a cooled central core, like the inside of a thermos, while the outer shell takes the heat. The instruments wouldn't touch the surface directly. Instead, they'd use extendable arms or robotic scoops to collect samples or take readings. These tools would move fast, do their job, then retract into the cooled housing. It's not unlike how some deep-sea probes survive pressure. They keep everything important tucked away in a protective core. Cables, joints, and motors all pose their own issues. Traditional electronics stop working well above 400 Kelvin. On Io, even a shaded area might exceed that. Standard circuit boards and batteries would fail quickly. New types of electronics are being developed that can handle extreme heat. Silicon carbide chips, for example, can operate at temperatures that would fry normal computer systems. These are already being tested for Venus missions, For Io, they could make it possible to run basic controls without bulky insulation. Most batteries degrade rapidly in heat. Lithium-ion cells, used in many space probes, can swell or catch fire at high temperatures. Safer alternatives include thermal batteries, devices that remain inert until heated, then deliver a quick burst of power. These are commonly used in missiles and could be adapted for a fast, high-heat mission on Io. Another option is fuel cells, which generate electricity from chemical reactions. These systems could work well in sealed environments, where heat is managed and oxygen is in short supply. Io's surface is coated with fine reactive grains of sulfur and silicates. These particles can stick to surfaces, block vents, and act as abrasives. Any cooling system that uses fans or moving parts could jam quickly. Systems need to be sealed, smooth, and easy to clean. Some future probes might use magnetic or electrostatic fields to repel charged particles. Others could carry disposable protective covers that peel away once operations begin. Rather than building something that lasts for years, the focus shifts to something that gets results fast. The idea is to cram as much science as possible into the shortest time window. Maybe it lands, drills once, takes a temperature reading, and sends the results before melting down. That might sound wasteful, but if the data is good, it's worth it. That mindset leads to modular designs, robots made of swappable units. If one part fails, another can take over. A heat-damaged camera could be replaced by another on a different arm. Instruments could be duplicated in different thermal zones, each working for as long as it can. Some systems might be shielded, others exposed. This flexibility means more chances of success, even if conditions turn out worse than expected. Communication gear must also be thermally protected. Antennas that overheat can lose signal strength or warp slightly, making it hard to aim transmissions. Some ideas include fold-out dishes that stay folded until the last minute. Others propose hardened antenna arrays, wrapped in reflective coatings and pointed away from lava flows. The key is timing, sending data while the system is still cold enough to function, before the buildup of heat shuts everything down. Heat-tolerant robots could open new doors not just on Io, but in many extreme places. Mercury's dayside, Venus's highlands, even the dark skies above solar flares, all could become reachable if these thermal systems proved themselves. But Io might be the ultimate test. It's not just hot. It's chaotic, unpredictable, and alive in a way most space environments are not. Sending a machine into that environment means accepting risk, preparing for failure, and designing around limits. Every component must have a purpose. Every second of operation counts. The lava won't wait. And the data, if we can get it, might reshape what we know about active worlds, not just in our solar system, but across the universe. Terraforming the untamable. Could we ever colonize Io? Could we ever live on Io? Not just survive, but stay. To imagine human settlers on Io, the first thing that needs to be addressed is radiation. A human standing on the surface would absorb a lethal dose in less than a day, without protection. Even thick metal shielding might not be enough. For a permanent base, this problem can't be avoided. It has to be solved. One proposal is to build underground. A colony buried beneath the surface could be shielded by layers of rock. This idea works well on the Moon or Mars, where lava tubes offer natural shelter. But Io's surface is unstable. The crust can crack open with little warning. A buried base could be crushed or cooked from below. Engineers would have to design a flexible system, something that can detect movement and adjust its shape, or even relocate if needed. Another idea is to build radiation shields above ground using powerful magnetic fields. These would mimic Earth's own magnetic field, deflecting charged particles away from a habitat. This approach has been tested in space on a small scale, but never on a planetary surface. To work on Io, the system would need to be much stronger. It would also have to resist interference from Jupiter's own magnetic field, which is constantly shifting. Running such a system would take a lot of power, and it would need to stay online at all times. Even a short failure could be deadly. Then there's the volcanoes. A colony would have to avoid these danger zones completely. That means staying away from active regions, which isn't easy because much of the surface is active. Some scientists have proposed using satellite images to identify long-term cold zones where activity is lower. Others suggest building floating bases, platforms that sit just above the surface on thick legs or even hover using magnetic repulsion. These designs could move if a volcano flares up nearby, but again, the energy demands are high. An even more extreme idea is to change Io itself. Some have proposed using massive orbital mirrors to redirect sunlight away from the surface. This would lower surface temperatures, possibly even freeze parts of the lava flows. Others suggest the opposite, using the mirrors to heat specific areas, forcing eruptions in controlled ways and creating safe zones elsewhere. This kind of terraforming is far beyond current technology. The mirrors would have to be hundreds of kilometers wide, precisely aimed, and able to adjust as Io moves. The timing would have to be perfect, and the results would be hard to predict. Still, it's an idea that has been discussed in theoretical papers. Magnetic shielding could also be attempted on a planetary scale. If a massive artificial magnetic field were generated between Io and Jupiter, it could theoretically deflect radiation away from the entire Moon. This concept has been studied for protecting Mars, and some researchers think it could be scaled up. But to work for Io, the system would need to be even more powerful. It might require satellites in orbit around Io, all working together to create a bubble of protection. These satellites would need constant maintenance, and any failure could expose the colony below. Io doesn't have much in the way of water. It may have small amounts of ice locked in the ground, but not enough to support a colony. Water would need to be imported from elsewhere, maybe Europa, or from comets redirected into orbit. Food production would also be difficult. Plants don't grow well in low gravity or in sulfur-rich soils. Farming might have to happen in sealed greenhouses using hydroponics or imported nutrients. Power could come from nuclear reactors or possibly from harvesting heat directly from the volcanoes. Living on Io would mean constant danger. The land could shift beneath your feet. Toxic gases might leak into habitats. Radiation storms could strike without warning. Colonists would have to be trained like submarine crews or astronauts, ready to act in seconds if something goes wrong. Systems would need backups and fail-safes. Nothing could be left to chance. And yet some might argue that Io would still be worth it. A station on Io could serve as a research hub or launch point. It might help scientists study volcanism, radiation, and tidal heating up close. It could also serve as a test bed for technologies needed on more distant worlds. If humans can build a base on Io, they can probably build one anywhere. Would people want to live on Io? Would the risks be worth the reward? Colonies need more than just air and water. They need purpose, connection, and meaning. Io might appeal to explorers, scientists, or those seeking a challenge. But it's unlikely to be a place for families or long-term communities, at least not in the beginning. These visions of a colony on Io would require breakthroughs in energy, materials, automation, and environmental control. But it's not impossible. The same was once said about space stations, moon landings, or robots on Mars. Every big step begins as an idea. And as wild as it sounds, colonizing Io is an idea that forces engineers and scientists to push the limits of what's possible. Some architects have sketched out future habitats for Io. These include domed cities with radiation-shielded walls, pressurized lava tubes turned into living quarters, and even mobile crawler stations that inch across the landscape avoiding danger zones. These designs may never be built, but they help people think about what life might look like on a world that never stops changing. In many ways, Io is the final boss of the solar system. Colonizing it would be about determination, about proving that life can find a way even in the most violent places imaginable. And in doing so, it might teach us something about our own planet, how fragile it is, how precious, and how much we take for granted when we step outside and breathe clean air under a calm sky. What other places in the solar system would you like to travel to next? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.